Okay. All right. Any questions on chapter 6 and 7 that you read over the week that I can make sure I don't gloss over? Everybody understood it? All right. Well, we're done. Let's go.
Can you go over what systems we have for the road tax and
Yes, I'm going to go over that. So road tax specific. Road tax specific. Questions? Okay. Yep. I'm going to talk about those in detail because they are different. Some of them are way different than your typical Lycoming or Continental engine, so I'm gonna take some time with that. What else? Anybody else have questions that I want to make sure I don't gloss over? Yes, sir.
Name?
Sorry?
Your name?
David. Sorry, and your name?
Paul.
Paul. Nice to meet you, Paul. Got a couple of new. You're new? Were you here last week?
I was here last week.
You were here last week. Okay. There's so many. There's a lot of new faces, so it'll take me a while. Any other questions regarding chapter 6 or 7 before we get into it? All right. So it just sounds like road tax specific stuff. As I said last week, if you have questions while I'm going through anything, stop me and ask me. If you have the question, then that means somebody else has the question. And if you don't ask it and they don't ask it, nobody asks it and it doesn't get answered. So make sure you ask the question. All right. So we're going to first talk about flight controls. I want to jump to this page just real quick here, and we talked about this a little bit last week, but I want to review it again. The axes of the aircraft. There's 3 axes, right? We've got the axis that runs from the wingtip to, not really wingtip to wingtip, but in this direction, called the lateral axis of the airplane. So it's going in this direction like this. That's the lateral axis, and we pitch the airplane nose up, nose down around that axis, okay? And the flight control, the primary flight control that we use to do that is back here, this movable section back here on the back of the horizontal stabilizer called the elevator, okay? So that's the elevator. And we have an axis that runs straight up and down called the vertical axis. And what's the movement around the vertical axis? Yaw. And what primary flight control do we use to control that?
Rudder.
The rudder, all right? And then we do this. What do we call this action? What do we call that movement?
Roll. Okay.
Roll, and what's the axis? Longitudinal axis, okay, and what are the control surfaces we use? Ailerons, the ailerons, okay. I jumped into that and I forgot I forgot I was going to ask you guys some questions about last week to see how much of what we talked about last week stuck, and we did talk about this, so that's okay. So, question for you. What are the 4 forces?
Thrust, drag, lift, weight,
Okay. When are they in equilibrium?
when everything equals 0.
No, the opposite forces are equal.
Okay, so what's equal to what?
The lift is equal to the weight, and the lift is equal to the drag.
Okay, and can that be the case if you're climbing,
Yes.
descending?
Yes.
Okay. What did Bernoulli say?
Venturi,
Okay. Now that wasn't Bernoulli. That was continuity. What did Bernoulli say? What was his
That,
principle?
faster than air going over an object could like release some drag pressure on it.
Decreases the pressure. Okay, that's correct. All right. So then, generally speaking, if you just had to sum it up into just a real quick, easy sentence, if you had to tell somebody, how does a wing generate lift in just one real quick sentence?
Low pressure on top, high pressure.
You're smart kid over there. All right, what's the definition of angle of attack? Anybody but, what's your name again, Jacob? Anybody but Jacob. Jacob knows the answer.
Chord line in relation to relative limits.
Chord line to relative. I'm not picking on you, but you do know the answer, so I got to let somebody else answer. Okay. All right, and what is a stall?
The wing fails to produce lift.
Okay, and when does that occur?
When it exceeds
Critical angle of attack. What speed does that happen at? Any speed. Okay, good. All right. What are the 2 types of drag that we experience on an airplane? Induced and parasitic. Interference is part of which one of those 2? Parasitic. Parasitic drag, right. Okay. All right, good. You guys were listening, or you were reading or something. How do those two, how does parasitic and induced drag, how do they differ? How are they different from each other?
Induce is when you get slower, predominantly.
Okay.
And, interference, sorry,
Parasitic?
parasitic drag is when you get faster.
Yeah, so parasite drag increases as our speed increases, induced drag increases as our speed decreases. So they're inverse to each other. Okay, and what's load factor? What does that term mean, load factor? Talked about that last week. That's an important
The wing has to support.
Okay,
How much
all right.
more force the wing has to support.
Okay, and when do we, what kind of things can we do to put load factor on the airplane?
Flying turns predominantly.
Okay, turns, yeah, all right. And what happens, does load factor have any effect on stall speed? How?
Absolutely.
Huh? It increases as load factor goes up, stall speed increases. Okay, good. All right. All right, good job. Okay, so we're going to talk about the primary flight control surfaces first before we get into systems. And I want to just kind of throw this diagram up here. This is just an example of a control stick connected to an elevator and one particular way that it might happen. There's multiple ways that you can actuate the primary flight controls. So what are the three primary flight controls, first of all? We just talked about them. They control us in pitch, roll, and yaw.
Rudder, elevator,
Rudder, elevator, and aileron, right. So we have controls inside the airplane. We'll either have a stick or we'll have a yoke, okay? And then we'll have rudder pedals on the floor. And what this is showing you is just different ways that we can connect the stick or yoke and the rudder pedals to the primary flight control systems. So if you were in the emergency class a few weeks ago, we talked about control system failure. Remember that? For those of you guys who were in it, we're talking about maybe a locking of a rudder or elevator or aileron, all right, and how dangerous that might be, okay? Well, one of the reasons it's important to understand systems is that if you understand how, when you move the control in the cabin, how's it causing the rudder, aileron, or elevator to move, can go a long way towards helping you diagnose something that could be occurring, okay? So unlike driving a car, how many of you ever changed the oil in your car? Okay. How many of you know where you would go to do it even? Okay. How many of you know how many cylinders you have in your car? Okay. So the point is, not a lot of us really care to know too much about our vehicles or the systems in our vehicles, right? Because if something happens, you just pull over the side of the road or you go to a mechanic or do whatever. If you're flying an airplane, you need to know a little bit more. You need to have enough systems knowledge where you can diagnose a little bit, what's going on. So the flight controls, it's important to understand how they're actuated. They could be actuated a bunch of ways. They could be a system of pulleys and cables or chains or things of that nature. It could be direct push-pull tubes. Could be electric. Could be servo motors, and you have an electric connection. Could be hydraulic. All right. There's a lot of different ways that you can control or you can move the primary flight controls by actuating the stick, yoke, or rudder pedals inside the airplane. It's important for you to understand how that's done. All right. So let's talk about our aircraft. When you move the rudder pedals, how is that connected to the actual rudder back there?
Sometimes it would be like a series of chains and inside the airplane.
But I'm talking specifically, you may not know because you're not flying our particular airplanes, but for those of you that are flying these airplanes, that pre-flight these airplanes every time you fly, how is it connected
Push rod.
to the rudders?
Oh, it's a cable.
It's a cable. There's a cable that goes to the rudder, all right? So when you walk around the back and you're checking the rudder, you see that little cable that wraps around the bottom. There's a little rudder horn down there, and that cable wraps around, and when you push the rudder pedals, it just pulls the rudder left and right. All right, what about the elevator? How's that connected?
That's a push rod.
That's a push rod. That's a push rod. There's no cables, no chains. It's push rods. What about the ailerons? Push rods. Okay. So the ailerons and elevator are push rods, or sometimes we call them torque tubes, but it's about a 1-inch diameter aluminum rod hollow rod that just is connected to the, directly connected. I mean, there are some horns in there that will change directions, but there's no cables or pulleys or anything like that. All right, so that's how ours are connected. And whatever airplane you're flying, you really need to know that. You need to understand how they're connected, how those control surfaces are connected. Okay, let's talk about secondary flight control surfaces. What are secondary flight control surfaces?
Trim.
Flaps and trim, right. So anytime we say a flight control surface, what we're saying is if you actuate or if you move this particular surface, there's going to be a change in pitch, roll, or yaw. So if I say a flight control surface, whether it's primary or secondary, there will be a pitch, a roll, or a yaw change as a result of moving this particular surface. The primary surfaces are aileron, rudder, and elevator, because that's our primary pitch, roll, and yaw. But if you trim the airplane, everybody who doesn't know what I mean by trim right just yet. Okay, I'm going to get to trim. But if you trim the airplane, you can do this in all three axes, pitch, roll, or yaw. And it essentially takes the control pressure off of the control that you're using. All right, I'll explain what it means in just a minute. So if I trim the elevator, if I use elevator trim, I'll get a pitch change. If I have aileron trim and I use aileron trim, I'll get a roll change. If I have rudder trim, I'll get a yaw change. Okay, and then flaps also have an effect on one of the pitch, roll, or yaw. Which one do you think it'd have an effect on?
Say that again?
Flaps, the flaps. Pitch, it would have an effect on pitch. Okay, why would it have an effect on pitch?
Oh, it increases lift.
Okay,
Increase lift.
it increases lift.
And reduce drag.
It changes it changes the center of lift. It moves the center of lift backwards, and you get a nose down pitch change. Yeah, that's what happens when you put flaps in. Okay, so those are your primary and secondary flight control surfaces that I want to talk about. And let's talk about now some specific types of connections here, or what's happening. Let me go here to the elevator. Here, let me show you elevator real quick. I kind of drew this on the board last week. I talked about how weight acts through the center of gravity, right? Lift acts back here, which would cause a nose down pitching moment. And then you have this tail surface that keeps the airplane from tumbling, right? This is my stabilizer back here. All right. So in this condition with the elevator like this, I'm getting a tail down force, which is causing a nose up condition, pitch condition, right? Everybody can see that pretty easily, right? So that's the purpose for all three of the flight controls, how they work. If I were to take this elevator as an example and just draw the elevator right here, all right? There's the hinge section. So this is the horizontal stabilizer. This is the elevator. This is the movable part. So this will move, like this. It could be up here like this, or it could be down here like this, right? As we're moving the stick, as we're pushing the stick forward and aft, or the yoke forward and aft, we're moving that flap, if you will, or that elevator on the back, okay? So how does this affect, what does this do to cause this pitch change? Well, when we're in the neutral position right there, if I look at this as an airfoil and I draw my chord line through there, what kind of airfoil is that? We talked about these two types of airfoils. We talked about, this is a symmetrical airfoil. So what does that mean with the airflow going over the top and under the bottom? Is there going to be a pressure differential here? It's going to be equal pressure, right? Because there's no camber, there's no curvature greater on one side or the other. But as soon as I do this with the elevator, in this example, as soon as I do that, now I have camber here. Now where do I have low pressure? On the bottom. I have low pressure here. I have high pressure here. Where does the tail go? That way. And the nose pitches up. Okay, when I go the other direction, when I move the elevator here, I have camber here. Now I have low up here, high down here, and the nose pitches down. Okay, so that's how we operate. That's how the control surfaces operate. It's not that you're deflecting air. It's not like you might think, well, when I put the elevator here, I'm deflecting air and pushing the tail down. That's really, you're doing some of that, but it's primarily Bernoulli at play. Okay, you're generating a lower pressure in this case here or up here, and causing the tail to do this, which causes the nose to pitch up and down. Does that make sense based on our conversation last week on how air pressure causes how curvature of the airflow causes high and low pressures? All right. So you can look at this and turn this now into a rudder. Think about it the same way. You're looking straight down. You're looking straight down at the rudder. Here's the movable surface. Now we're controlling yaw. If we kick the right rudder pedal, the rudder goes over here. Where do we have low pressure? Down here. So the tail goes this way and the nose goes to the right. We push the left rudder pedal, goes this way, low pressure here, the nose goes to the left. Okay, so all we're doing with these control surfaces is we have a little wing back there. We've got little airfoils back there. Okay, they're symmetric. They don't have to be unsymmetric like this. If you recall, why does this generally unsymmetrical? So it produces lift at zero angle of attack. We can have a zero angle of attack and still produce lift because we have that increased camber on the top surface, right? Okay. And then ailerons are going to do the same thing. If you can, now you can imagine this being our wing, although in this case, our wing is typically an unsymmetrical airfoil. So you have a wing airfoil that may look like this, okay? So you have an aileron over here, and when this aileron is down in this direction, the aileron on the other side is up in that direction. That's what causes the roll, okay? So if we look at our airplane, if we want this guy to roll, if we want it to roll in this direction, we're going to move this aileron down, which causes more curvature here. We're going to move this aileron up, which causes more curvature here. So in this case, I've got lower pressure over here, up here, and in this case, I've got low pressure down here, so the airplane rolls in this direction. This wing gets lifted, this wing gets lifted, this wing gets pulled down. And in the opposite direction, it does that. So that's how we get that roll effect. Now the problem with roll, with banking the airplane when we have an airfoil like this, which most general aviation airplanes have, is it sets up something called adverse yaw. How many of you have heard that term? What is adverse yaw? Anybody know?
It's when you bend it and like the drag on the wing is greater than the other.
That's
so
exactly right.
Tendency to, I think, turn to the wing that's higher.
So that's exactly right. So adverse yaw is any yaw that you don't want. It's adverse to what you want, right? So what adverse yaw does is, as we want to turn this way, when we want to turn this way, the nose goes that way. When we want to roll this way, the nose goes adversely. It goes adverse to the direction of turn. All right? The reason it does that is because when we generate lift, what else do we generate?
Drag.
We generate drag. The more lift we generate, the more drag we generate, okay? So which one of these wings, this one or this one, is generating more lift? This one, if this is my lift vector, let's see if I can do this. That's my lift vector on that wing. This is my lift vector on that wing. So this one's generating more lift in this direction than this one is generating in that direction, and this wing gets pulled backwards. Okay? That's adverse yaw. And the reason it's generating more lift is because you have a more efficient curvature. So this curvature here, if you follow this curvature on this wing, let's say we're looking at this wing right here, this wingtip right here. So we're trying to roll this direction, okay? So this aileron is down, and here's the airflow. We're just gonna look at the airflow over the top surface. There's your camber right there, okay? The other side is generating lift in the other direction, and here's your camber in the other direction. Which one of these looks like a more efficient camber? Okay, yeah, this has more curvature than this one does. So this might be generating, let's say in vector form, that much lift. in that direction. That's the far wing. And this wing on this side may be generating that much lift. Okay? So as this wing, the blue side, is going up, it's generating more drag than this one is. So as that happens, it pulls this wing backwards. That's adverse yaw. Okay? This is why we have rudders on an airplane. Rudders are on the airplane to counteract adverse yaw. That's the reason for it. When the Wright brothers first started figuring out the control of airplanes, they did not have rudders. They had an elevator in the front, it was a canard design, and they had the wing warping. They didn't realize they needed anything for yaw. This was in their gliders. And so as they did their gliding experiments, as they went to warp the wings and turn this way, what would happen was the airplane would whip back in the other direction, they'd crash. And they figured out the aerodynamics of what was going on, and then they added a rudder to stop that from happening. That's how we ended up with rudders. Okay, so that's what adverse yaw is. When you have a flat bottom airfoil or an unsymmetrical airfoil, as you bank that airplane, the wing that's going up is generating more drag and it's pulling us backwards. And so we step on the opposite rudder to keep the nose from going backwards. We use a little opposite rudder until the bank is established. Once the bank is established, we can let off both the ailerons and the rudder, right? And then we just initiate let the turn continue. You don't keep the aileron in or you just roll right over, right? And you don't keep the rudder in or you just, nose down. Okay, so you use those controls, use both aileron and rudder as you enter into a bank or bring yourself out of a bank. Okay. Let's look at a situation with a T-tail. There's a lot of GA airplanes that have T-tails. There's quite a few different empennage kind of designs that you could have. You've seen your standard configuration looks like this, right? They have something called a cruciform where the horizontal stabilizer and elevator is kind of in the middle. All right, and then you could have a T-tail up like this, or you could have a V-tail like on Bonanzas. All right, there's a lot of different designs and ways you can do it, but one thing that you want to be aware of if you're flying something with a T-tail, and there's a lot of them out there, is that if you get a high angle of attack, like in a stall, the burble and the wake that's coming off of the wing can actually kill any effectiveness of your elevator, okay? So the reason this is in the book is because there's a lot of GA airplanes that have this type of configuration, and if you load this guy with an aft CG, we talked a little bit about loading last week, right? In an aft loading, if you get yourself into a stalled condition and your elevator is blocked, now you can't get the nose down. You try and push the nose forward to get some elevator effectiveness, nothing happens, and you just fly that thing right. You could fly it right into the ground because there's no way to get the nose back down if you're not properly loaded. If your CG's in the right place where it should be up here, and you got yourself into a stall, then the weight of the entire stable airplane would cause the nose to come down on its own. Okay, so be very wary if you're flying a T-tail airplane. Be real careful about your weight and balance. Okay, you get into a stall and you may not get out of the stall. All right, one other type of horizontal stabilizer elevator or a trim combination is called a stabilator. A stabilator, this is your horizontal stabilizer, and this is the trim tab back here. I'm going to talk about what trim is in just a second here. The difference between this, and you see these on Pipers, a lot of Pipers have these. You also see it on the Cessna, the Cardinal, the 177, this has this kind of type of stabilizer. Rather than having a fixed horizontal stabilizer with a movable elevator, the entire thing rotates. The entire surface rotates. It's called a stabilator. As opposed to a stabilizer with an elevator, it's a stabilator. It's all in one. As far as differences, practically speaking, for you as the pilot flying the airplane, you're not going to notice any difference whatsoever. You'll not even know that there's a difference there, the way it's designed to work. Okay. it has a what's called an anti-servo tab along the back. All right, so this functions as your trim tab. Okay, so let's talk about what a trim tab is and why that's important. I think I have a slide on it. Yeah, right here. Okay, so here's a trim tab. All right, so let's look at the elevator here. All right, and let's say that we're in this position, so we're pulling aft stick or aft yoke. Okay, so we're in this situation, we're wanting a nose up pitch, or we're wanting to go in that direction. Okay. We can do one of two things, and let's say that because of the way the airplane's loaded, let's just say for a minute that in order to maintain flight with our power setting, we need the elevator in this position right here to maintain this altitude, this flight condition. We need the elevator right there. We can do, and we're flying a long ways. We can do it like this. We can grab the stick and hold it, and just hold it there. Okay. Until our arms get tired. You know, if I take even this basically empty bottle of water, and I hold it like this, it's pretty easy to hold. But after about an hour, my arm's going to be burning and things are going to be hurting, right? It's the same thing with this. If I can hold the stick or I can hold the yoke there, right? But after a while, I'm going to start relaxing. It's going to become very uncomfortable. I really would like to be able to let go of it. All right. So let's look at the aerodynamics that's happening right here. Think about the airflow around this flight control here. Here's my flow this way, right? And that way, so my low pressure is down here. My high pressure is up here. So the entire elevator stabilizer system is moving in that direction, right? Everybody see that? Okay, so I can hold the stick there or the yoke there and let that happen, or I can use the trim tab. The trim tab is another little tiny flight control surface on the elevator that would then go that way. All right, and now what's happening is as the air flows over this little surface right here, I get low pressure here, high pressure here, which causes the elevator to go this way. So this little trim tab flies the elevator, and the elevator flies the horizontal stabilizer. So by using that little trim tab, I'm able to trim off the pressure and let go of the stick, because that little trim tab keeps the elevator, rather than me holding it there, the little trim tab holds it there and I can let go of it. That's what a trim tab does. And you can have trim on all three axes. So you can trim the elevator, which is primarily just about every airplane, unless it's a very slow, lightweight airplane like an ultralight or something. Otherwise, just about every single airplane will have, at a minimum, elevator trim. Okay? And then the heavier and the more complicated and sophisticated the airplane becomes, now you're more likely to see rudder trim and aileron trim. So you can trim all three. So all three of the primary flight controls could have a trim tab on it that's actuated from inside the cockpit. Okay? All right. Our airplanes have elevator trim that we can control from inside the cockpit. How is that actuated? How's the elevator trim actuated? What's that? It's electric. It's electric. Yep. There's a little motor back there, and we have electric control. What about the flaps? How are they actuated? Same thing. They're also electric. Yeah. Okay. All right. You will often see you ever see something like this on the bottom? I'll show you where that is this piece right, well, it broke off. It was right down here. There's a little aluminum, there's just a little piece of aluminum at the bottom of the rudder right there. Just attached to the bottom of the rudder. That's a rudder trim, but it's ground adjustable rudder trim. All right. So a lot of airplanes, and a couple of ours, I think 261 doesn't have this, and I think 5021 might also not have this. But on the rudder, there's a little aluminum a little piece of aluminum sticking out. That's the rudder trim. And on one of the ailerons, there's a little piece of aluminum sticking out, and that's the aileron trim. And what you do, it's ground adjustable, so what you do in these cases, since you can't adjust it in the air, is you get the airplane in cruise flight. And you figure out, okay, am I having to hold a little rudder? Am I having to hold a little aileron? And if you are, when you get on the ground, you bend that little tab a little bit. Then you go fly again until it's all straight, and that's about right. And then so it's a trim mechanism that you can adjust on the ground. Okay. The lighter weight and the slower the airplane, the less we need, the less power, and the slower the airplane, the less we need, or the less a rudder trim is really necessary. Actuated from inside the airplane, the less it's necessary. And aileron trim, the less it's necessary. Okay. The more power you have in the engine, the more rudder trim is needed. Why do you think that is? Left turning tendencies. Absolutely right. You get a high powered engine, propeller driven engine, it's going to have a lot of torque, a lot of left turning tendencies. And in that case, you roll full right rudder trim in and you take off that way. And then as you roll into cruise, now you take that trim back out, or else now it wants to go to the right. Okay. All right. Any questions on those? I didn't want to spend a whole lot of time on this because it's kind of common sense stuff. There's not a lot there. But I'm saying that, right? I've been doing this a long time. Does this make sense to everybody? How the primary flight controls work, how they generate high and low pressure based on this, the physics we talked about last week? Okay. All right. Trim, for those of you that didn't understand what trim is, do you understand? I don't remember who all raised their hand. Do you understand what trim is now? Okay. It's one of the most important things you're going to learn how to use, like immediately when you start flying, is trim. Like one of the most important things. Okay.
Like, go back to the slide right before this one.
Before this one?
Show that very.
The trim?
Yeah. Okay, from the way you're showing it right there.
I'm showing this one.
Yeah, that the low pressure is high and the high pressure is on the bottom part of it.
Yeah. So the green. So here you've got low pressure here, high pressure here because of this curvature, which is causing the tail to go down, the nose to be up. Okay. But to do that, I have to have the elevator in this position, but I don't want to hold it there. So now I use this little.
So you're just combating. I see. It's just combating a little bit of that.
This little airfoil right here is causing the elevator to stay in this position, and the fact that the elevator's in that position is causing the whole tail to go down. So I can either hold it. I can either hold the elevator here with physical force, or I can move that little tab there, and then I can let go of the elevator, and that little tab holds it there.
It's just enough to take that.
It just takes takes the pressure off the stick. Yeah.
Yeah, but if you think of it a little differently, it kind of gets confusing. Because right now, what you're saying, the high pressure is on the upper portion of the elevator. Thus, it's going to push more.
The high pressure's
on the bottom.
the high pressure's on the upper surface of the stabilizer.
Right.
Here, the high pressure's on the bottom side of the elevator.
Which is just it's taking away some of that lower pressure influence.
Yes, a little bit. Yes, it's whatever you need.
But what I'm saying, when you think of it intuitively, if you want to raise your nose, you're thinking maybe the other way of doing your trim tab. You have to kind of keep that in mind.
Yeah, just remember the elevator. The elevator flies the stabilizer,
Right.
and the trim flies the elevator. Okay, or the primary flight control flies the stabilizer or the wing if it's an aileron, and the trim flies the flight control. Okay.
No, it makes sense.
Okay. All right. Any questions on what we did there? I want to move into the systems a little bit here. Okay. All right. Okay. So let's move into systems. So when we're talking about systems on the airplane, generally speaking, we think about, okay, the engine and all the associated systems that go into keeping that thing operating. And that's the majority of what we'll talk about. But there's other things. There's electrical systems, right? We do have a hydraulic system on the airplane. You know what that is? Brakes.
Yeah, brakes.
That's it, just brakes. That's the only hydraulic system, right? So we do have electrical system. We have, there's other systems, fuel systems, right? But that feeds the engine. But generally speaking, when we talk about systems, we're talking about those things that are necessary to feed the engine, okay, or the whatever the thrust producer is. And on general aviation airplanes, it's typically an internal combustion engine. Doesn't have to be. I mean, airplanes, they could be reciprocating combustion engines. They could be jet engines. They could be rocket engines. It can be a lot of ways that you produce the thrust. But we're going to talk about reciprocating primarily four-stroke engines because that's what you find on most general aviation aircraft. Okay. One of the things that I'll tell you with respect to systems, it's a weak area. A lot of people have a hard time with it. If you're not a mechanical by nature, sometimes you can have a hard time with this subject area. You don't have to be a mechanic, but you need to understand enough about the systems that you can do some troubleshooting, some things. All right. Not that you got to go out there and put a wrench on it, but you need to be able to have some idea of what might be happening, and that's the purpose for this. For those of you young guys that want to go and go to the airlines or go farther, systems is really important. As a matter of fact, when you get your type ratings, once you're an ATP, airline transport pilot, let's say, and you're flying in a 737 or something like that, well, you can't just go fly a 757 or a 727. You have to be typed in that airplane. And type ratings aren't about learning how to fly the airplane. There's some of it. Type ratings are all systems. What are the systems on this airplane? What are the systems on this airplane? How do I get fuel to the engines from this in this airplane? How do I get it in this airplane? So it's all about systems. So for you younger guys that are going to be airlines or go professional, start paying attention to systems because you have to understand how systems work. Okay, reciprocating engines. Used to be we had rotary engines like this. You see those back on like the World War I airplanes. And they were air cooled, obviously, and these cylinders all just stuck out in the air, so it was easy to keep them cool. And the design was such that they were pretty compact because they were all laid out radial around the crankshaft. Primarily now what we have are engines that look like this. They're horizontally opposed, and we call them flats, or this might be a flat 4 or a flat 6 or a flat 8. And by that, it just means the location of the cylinders. So these cylinders are in a flat formation as opposed to like a V. You've heard of a V8 or a twin V or whatever. The other was a radial, okay? You could have an inline where all the cylinders are just in line with each other. But typically in GA airplanes, we have horizontally opposed, just like this one, horizontally opposed flat 4, which is what this one is. So you've got 2 cylinders here, you've got 2 cylinders right behind it. Flat 4, okay? All right, so this is primarily what we're going to be talking about. All right, let's talk about the operating principle of a 4-stroke engine. So these are 4-stroke engines, and let me grab a cylinder here and a piston so I can talk about this. Okay, here's a cylinder off of one of our Rotax engines. Here's a piston. So this is what I'm holding is this part right here. This is the cylinder barrel, okay? This is the head of the cylinder. You grab a head here. Okay, here's a head, all right? I'll put that on there in just a minute, but that's the head of the cylinder and it goes up there, okay? All right, so 4-stroke operating principle. Intake, compression, power, exhaust. That's the 4 strokes. Intake, compression, power, and exhaust, okay? So what we're doing is we're moving this cylinder, or we're moving the piston in the cylinder such that we're intaking air and fuel. Then the piston moves back up and we compress the air and fuel. Then we light the spark plugs and an explosion happens. That's our power stroke. Then we move the piston back up and we push all of these spent gases back out. So that's the intake, compression, power, exhaust. Okay, so so the full cycle is the piston starting at the top. Picture the piston inside here. The piston starting at the top of the cylinder. We intake, we compress, power, exhaust, and then just back and forth, back and forth, back and forth. That's the 4 strokes. Okay, so I'll get a little deeper into this, but those are the 4 strokes. We need 3 things to make an engine run. We need 3 things, 3 ingredients: air, fuel, spark. We need air, we need fuel, we need spark. So we're going to talk about these 3 systems, okay? That's the intake system, that's the fuel system, and that's the ignition system. And we'll talk about them all together, but I want to use them in this as this example of how this works. When we intake, what we're doing is we're opening what's called the exhaust valve. So let's look at the top of the cylinder here. You see the top of the cylinder? This is where the piston ends up here. So this is the top. There's intake, compression, power, exhaust, okay, inside the cylinder. You see these 2 valves right here. If I was strong enough, you've got heavy springs on them. I'm not strong enough to push them out, but yeah, I can't push them out.
They're pretty good.
Yeah, they're pretty tough. That's a pretty thick spring. All right, so this is the intake valve right here in the top of the cylinder. This is the exhaust valve in the top of the cylinder head, or this is the head. This is called the cylinder head. All right. So what happens on the intake stroke, before anything happens, the piston is all the way up here at the top. We'll call it top dead center, okay? As this stroke begins, that intake valve opens. So this valve opens, and you get a little opening there. This pulls down. This is coming down. As that's coming down, I want you to think about a syringe. Think about this as the syringe. As you're using a syringe and you pull down, it's sucking stuff in, right? So what's being pulled in is fuel and air. The fuel and air has been mixed in the carburetor. We'll talk about that as we go along here. But the fuel and air mixture has been mixed, and it's delivered into the cylinder. As this is coming down, we're pulling that fuel and air mixture into the cylinder. As soon as this piston gets to the bottom of the stroke, the exhaust valve closes. Now we've got both of them closed, so we have a sealed, well, somewhat sealed cylinder or chamber. All right. Now we begin the compression cycle. This comes up and it compresses the fuel and air mixture. Okay. Just before we get to the top, there's 2 spark plugs in this top of this head here. You can see them right here. There's a spark plug. There's a spark plug right here, and there's a spark plug right there, and you can see them right there and right there. The little spark plugs. Okay. So as soon as this thing gets just about to the top, not quite all the way to the top, but real close to the top, that fires. Those 2 spark plugs fire, and we have an explosion. We have a burning of that fuel air mixture. That causes a rapid expansion of the fuel air mixture because of that explosion, and pushes this piston down. As it pushes that piston down, the piston is connected to the crankshaft, which is turning the whole engine, right? The crankshaft is connected to the propeller. And so this is turning, right? As that's happening, that's turning, okay? All right, so that's our power stroke. Boom. This is getting pushed down. That explosion pushes that down. Right as we get to the bottom of that stroke, now everything's still closed. The valves are closed. As we get to the bottom of the stroke, the exhaust valve opens. Okay? Now we push this back up and we push all that exhaust out. Both valves close and we start over again. Okay, that's our 4 strokes. So we intake, we compress, we explode it, we get the power stroke, and then we exhaust it back out. Okay? That's how your car works, unless you have a, well, even if you have a diesel engine, it's just a little bit different, but that's how it works.
Different fuel.
Different fuel, yeah. And a different ignition, you don't have, it's the compression causing it, yeah. All right. Any questions on that so far? No? Okay, all right.
Actually, I have one more.
Okay.
How do the spark plugs know when to fire? Is it like
We'll get,
racing?
okay, so when we get to the ignition system, I'm going to answer that question. Okay? Okay, yes.
So when you use throttle, is
that controlling the amount of fuel and mixture coming into that cylinder?
When you use the throttle, you're controlling the volume of the fuel-air mixture. The volume that's going in, right? Okay. And we're going to be getting to that as well. Okay. So, got this pretty good. Intake, compression, power, exhaust. Okay. So we got to have an intake system. We got to have to bring the air in. So the intake system is the air coming in. Got to have fuel to mix with it. Got to have a spark ignition, and then we'll talk about the exhaust system as well. All right, but I want to talk about what happens to how do we get the power? Okay, so as this four-cylinder engine is firing, okay, and by the way, not all four cylinders are firing at the same time. They're all at a different place. So one of them's power, one of them's intaking, one of them's compressing, one of them's power, one of them's exhausting, right? So you're only getting power out of one of them at a time. Okay? The other four or the other three are in one of the other strokes, but they're just happening over and over and over again. All right. So the piston is connected to a little push rod that's connected to the crankshaft, and that's turning the crankshaft. The crankshaft is connected to, or the propeller is connected to the crankshaft, and the propeller is turning. So this is what's giving us the thrust in a propeller-driven airplane. The engine's supplying the power, the propeller is supplying the thrust, and that's the force, right, that we need to overcome drag. Power is not a force. Thrust is a force. Okay. So how does that work? Well, we talked about this last week. Remember how we need different airfoil shapes at different angles of attack along the span of the propeller in order to give us somewhat even thrust along the propeller? Okay. All right. Anyone need a refresher on that before I move to what these two instruments are? I will if I need to. Understand that? Okay. All right, let's look at these two instruments. These are power indicators for us. We have an RPM gauge, revolutions per minute, and we have manifold pressure. Those are two power indicators that we have. And the type of power indicator we have, or the type of power indicator typically that we're going to use, will depend on the kind of propeller that we have. So there's basically two kinds of propellers. What are they? Fixed
and
constant speed.
Constant speed.
Fixed pitch and constant speed. So let me grab the little fixed pitch propeller real quick. Hey, stranger. Okay, so here's a fixed pitch propeller. Okay, so this is what we have on our airplanes. And what that means is you can't change the pitch. You can't change the angle that the blade is set at relative to the hub, okay? This one's carved out of wood. Ours, the little piece here we have is carved out of wood as well. But the propellers we have on the planes now, we actually can change the pitch, but not while the airplane is running. We have to, while the engine is stopped, we can loosen some bolts and we can change the pitch and do things. But it's fixed pitch in the sense that we can't do anything about it while we're flying. RPM is measuring how many revolutions per minute this thing is turning. So from here, in 1 minute, every time this thing turns 360 degrees, how many times does that happen in 1 minute? That's the revolutions per minute, okay? If you have a fixed pitch propeller, your primary power instrument is going to be your tachometer or your RPMs, revolutions per minute. That's your primary indicator, all right? In this example, it's showing like 2,400 RPM, 2,400 RPM. On the Rotax, somebody asked how are we going to do Rotax specific stuff, so I will right now. I'll bring this in. The Rotax, this particular engine turns at cruise power at about 5,000 RPM. But there's a gearbox on the propeller that brings the revolutions per minute down to something that would keep the blades from separating because of the forces that would be going on there. If you had a propeller attached to that engine turning at 5,000 RPM, the speed of the tips would be so great you'd be breaking the sound barrier, and it would be a constant sonic boom as the propeller turns. What's that?
Like the XF-84, which is one of the USA that tried to make it.
Yes, there's a lot of airplanes that'll do that. When you hear warbirds and they have that really incredible sound, what you're hearing is not the engine. You're hearing the tips of the propeller reaching the sound barrier. That's what you're hearing. Is that. So you have to, when you're designing your propeller engine combination, you have to design the propeller such that you don't break the sound barrier. You know, when tip speed. So that's turning at 5,000 RPM. We cannot just directly attach a propeller to that crankshaft. Okay, you got to gear it down. You can't spin at 5,000 RPM. So that's what the gearbox is for. All right. A constant speed propeller, what it does is it allows you from inside the cabin, from inside the cockpit, it allows you to change the blade angle. Okay, on the fly, so to speak. You can change it on the fly. While you're flying, you can change that blade angle. And the reason that that's really particularly important is that any propeller engine combination is only going to be most efficient at one speed. Okay, at one speed. And so if you look at the thrust output of a propeller, as it's a combination. It's really a combination of the rotational speed, along with, you know, the angle of attack. And we'll usually take that at usually about 3/4 of the span. We'll say, okay, well, we're going to use that particular location. And if you look at the thrust output, it would look, this is speed here. Your thrust output might look something like this. So that would be the velocity that's most efficient for a fixed pitch propeller. If you have a constant speed propeller, as your speed increases, you can change the efficiency of the propeller. And you can get a more efficient propeller at different speeds along the speed range. So that's the advantage of a constant speed propeller. The problem with a constant speed propeller is that the RPM isn't as useful to you anymore for power output, because all this is telling you is how fast is the propeller spinning. It's not really telling you how much power is coming out of it. So let's talk about what that means. Constant speed propeller simply means that I can tell the propeller how many RPM I want it to turn, and it will stay at that RPM. Okay, given, I mean, there's points where if your power is too low, it'll drop off. But so let me give you an example of what I mean by that. When we're flying airplanes with a fixed pitch propeller, let's say you're flying along and you're at cruise and you got 5,000 RPM showing on the RPM gauge. All right, flying along and you pitch the nose up and you begin to climb. What's going to happen to you don't touch the throttle. What's going to happen to the RPM? It's going to drop. It's going to drop because you're putting an additional load on the airplane, putting additional load on the propeller. Okay, so it cannot maintain that 5,000 RPM. It drops off. The RPM drops. What if, same thing, if you push the nose over and you begin to descend, what will happen to the RPM? It's going to speed up. All right, it's going to speed up because you've taken load off of the engine now, and now the propeller can spin faster. All right. What a constant speed propeller does is it maintains that revolution. So if I set, let's say in this case, I set the RPM to turn, or the propeller to turn at 2,400 RPM, and I'm flying along and I'm turning at 2,400 RPM, and I pitch the nose up. Okay, what's going to happen is the blade angle is going to change so that it maintains 2,400 RPM. If I push the nose down, the blade angle is going to change so it maintains a constant speed. That's why we call it a constant speed. So it doesn't have to do with velocity this way. It has to do with constant rotational velocity. Constant rotational speed propeller is what that is. All right. So the reason now we need a manifold pressure gauge is this doesn't tell me how much power I'm outputting, because this is changing, right? So you can kind of think about it like a 10-speed bicycle, right? It's kind of like gearing your propeller, if you will. Everybody ridden a 10-speed bicycle or bicycle with more than one gear? All right. So the reason that's so efficient is that at slow speeds, you put it in one gear. Let's say that you calibrate your leg muscles and you can put exactly the same amount of power to the pedals. What you do with that power depends on what gear it's in. Okay, so that's one way you can look at this. What you do with the power, the manifold pressure, what happens given a manifold pressure, depends on where you set your blade angle. So the power you set here, the power you're giving, what happens with it depends on where you have your blade angle set, what gear you're in, so to speak. Okay? Clear as mud? Questions?
So which planes particularly have them?
Have a constant speed propeller? More high performance airplanes will have constant speed propellers. Yeah. High performance, some 172s could have them, but generally, like when you get into a 182, those will have constant speed propellers. And the way you'll know is when you look in, if you look in the cockpit of the airplane, typically you'll see three knobs. You'll see a black knob, you'll see a blue knob, and you'll see a red knob. Our airplanes, how many knobs do we got? We got one. We got a black one. All right. So this is throttle. This is propeller. So if you see a blue knob, you got a constant speed propeller. Red is mixture. We don't have a mixture in ours. And I'm going to get to why here as we get through this, but we don't have a mixture control in our airplanes. We only have a throttle. Okay. But if you're in most GA airplanes, if it's a higher performance with a constant speed propeller, you'll have a black, a blue, and a red. Okay? All right. So what is manifold pressure? Let's talk about what manifold pressure is. You know what a manifold is? Anybody not know what a manifold is? Okay.
The container of whether it's intake or out exhaust manifold.
Yeah, so it's basically if you take one distribution channel and you break it up into multiple channels, that's a manifold. So if you took a hose and you connected a couple hoses coming off of it, that would be a manifold. So that's all so this is an intake manifold as an example right here. This right here. See, that's a pipe comes in here and it splits into two. That's a manifold. It could have 4 or 10 or 15. It'd be a manifold. So if you take one delivery pipe or tube or whatever and you break it up and you multiply it into multiple places, that's a manifold. Okay. So the intake manifold. I wish I had all 4 turning wheels on this. See if I can get this spun around here. Should have it on this side. It's easier to see. Okay. Easy to see here. This is a carburetor right here. Okay. I'll go into those a little bit later, but the carburetor is where we mix the fuel in the air that ends up going to the cylinder for combustion. That's the carburetor. Once the fuel in the air is mixed, then it goes through the intake manifold and some of it goes to this cylinder, some of it goes to that cylinder. On the other side of the engine, we have another carburetor. This is another thing different about Rotax engines. We have 2 carburetors, not one. Most engines, you'd have one carburetor with an intake manifold that has 4 ports going into the 4 cylinders, or 6 if you have 6-cylinder. So here we have the carburetor. We have the fuel in the air going in here, or excuse me, the air going in here mixing with the fuel. Then it delivers it to the 2 cylinders. Okay? Just on this side of the carburetor. So let me draw here. Here's our carburetor, let's say. And then we have a manifold going into a cylinder. Here's one of my cylinders. Here's my other cylinder. Okay? So here's a cylinder, here's a cylinder. I've got fuel, I've got air coming in here. I've got fuel mixing with it. Okay? And that gets delivered to the cylinders. Okay? This is called a manifold pressure gauge. And what we do is we put a little, we read the amount of pressure basically right here at the intake manifold. Okay? So the amount of pressure of the fuel air mixture that's coming in here that's being delivered to the cylinders is being measured, and we're measuring it in inches of mercury. We call it manifold pressure. So in this case, in this example, the manifold pressure is 23 inches. 23 inches of manifold pressure, okay? So if I were to open the throttle wide open, I would end up with a higher manifold pressure. If I were to close the throttle way down, I wouldn't, this is the question you were asking a while ago, I wouldn't have as much pressure of the fuel and air going into the cylinders, okay? So this now is how I read how much power I'm sending to the cylinders. I read it through manifold pressure. How much am I letting fuel and air get to the cylinders, or how little am I letting fuel and air get to the cylinders? And we measure it through manifold pressure, okay? And it comes right here, right off of the intake manifold. And we have intake manifold, we have manifold pressure gauges on our airplanes. You guys just never look at it. You're always looking at the RPM. But it's coming from right here. If you look at this little tube right here, see this little tube coming right there, right off the intake manifold? And the other tube comes to the other intake manifold. They come together, and then there's a little line that goes to the sender, intake manifold sender, and we read it actually on the instrument panel. We never show it to you because we use, you can ask about it now that you know it's on there, we use RPM as our power gauge, but we also have a manifold pressure gauge that you could look at there, okay? So if you have a constant speed propeller, you can't use RPM because as you add power, let's say that you have your RPM set to 2400 RPM, and then you increase the throttle. Is that going to change? No, it's not going to change. The blade angle is going to change to maintain 2400 RPM, but you're sending more fuel-air mixture to the cylinders. So you're developing more power, but you're not changing the rotational speed of the propeller. It's just like keeping yourself in the same gear in your 10-speed, but putting more power to the pedals, or the reverse of that. Okay, so that's a constant speed, or excuse me, that's a manifold pressure gauge and how we use it with a constant speed propeller. All right. Any questions on that so far?
Well, I do have a question.
Okay.
Now that you say it has two carburetors.
Yeah.
The Rotax engine.
Yeah.
So now you have two separate systems that could be involved by icing. What's the likelihood of both of them getting, ice?
The likelihood would be that they would both ice up pretty much
would.
at the same time. Yeah.
Yeah.
Yeah. They'd both ice up. Yeah. Yep.
It just doesn't seem probable that both of them.
Well, they're both getting the air. So when we talk about ice, what's causing? Well, we're going to get there. We're going to get to the icing.
Okay.
Yeah.
Why do we only measure one cylinder head temperature?
We measure two cylinder head temperatures. The Rotax engine only has two cylinder head temperature ports. There's one right here. It's on the number 4 and on the number 2. And so for whatever reason, that's all they give us on the Rotax. A lot of engines you can measure CHT on every single head. Yeah. Rotax just gives us 2 ports, so we measure those 2.
In the plane we're flying, there's just one.
Well, we may only have one hooked up, and it'd be this one. It would be this one, number 4, because this is going to be the hottest cylinder because of where it's located in the cowling.
Okay.
So we would measure. So if you are only measuring one CHT, one of the cylinder head temperatures, you typically want to measure the hottest one
In the back.
in the back, and it's usually that'd be in the back. Yeah, yeah. Okay, let's take 5 minutes. And if you didn't sign in, that we put the sign-in sheet out there so that I could put the engine in here. And feel free to look at the engine there, and if you want to. So let's move to the induction system. All right, so the 3 things we need for combustion: fuel, air, spark. So induction system is responsible for the air. The induction system is how we induce or get the air into eventually, ultimately, the cylinders. We've got to get the air inside of here in order to provide for combustion. Okay, so we're going to talk about the induction system. The induction system on the airplane that you're flying, you need to be aware of. You need to know how it works and where it is and where the air is coming in at and where are the filters. There's going to be a filter. Understand that, right? The induction system is an open system. It's not a closed system. And what I mean by that is that it's going to get into the engine, right? Air is getting into here. So if the air that's coming in has flies and bugs and dirt in it, guess what's going in the engine? Flies and bugs and dirt. So we need filters there somewhere, right? So most induction systems, not most, all induction systems are going to have a filter, at least a filter someplace. If you're flying something like this, most GA airplanes, the filter, in fact, on this little Skyhawk, that little box you see down there, that's the induction system filter right there. It's right in the beginning, right in the front of the plane. Pipers, you see it all right there. On our particular airplanes, that's not where it is at. On our airplanes, if you look at the front of the cowling, all right, the spinner's right there. You've got an opening right here, got an opening right here. Looks like that. Does that look kind of familiar to you a little bit? Right here, that's induction right there. That side as you're looking at the front. That's where the induction air is coming in, okay? If you look in there, you'll see a little duct, a little round duct, about 2 inches, 2.5 inch diameter duct. That's coming in basically right here. It's coming in right here, okay? And then there's a flexible duct that goes from there and it comes up over like this and then goes right in the top of an air box. There's a box that's another manifold that manifolds into the two carburetors. So that air duct goes into the top of this box. In the top of that box is where the filter is located. And it's one of those cone-shaped, you ever seen those cone-shaped motorcycle K&N filters? Like a cone shape? That's the filter right there, okay? From there, once it goes into that little manifold, then it manifolds out and goes into the two carburetors, right? In the carburetor, we mix it with fuel, or the carburetor mixes it with fuel, and then that gets sent to the cylinders, okay? So the induction system is simply, we got to bring air into the engine for combustion. That's what the induction system is. On our airplane, right there, comes in right there. Yeah.
Does carb heat come in there as well?
Carb heat does come in there as well. What happens is right behind this little intake, or right behind that little duct, is a little box, okay? And when you turn, and there's a little flap in that box. When you pull the carb heat knob, that flap blocks the air from coming in here, and it takes air from inside the engine cowling. Heated air from inside the engine cowling. We essentially point it at the exhaust on this side, the exhaust manifold coming out of here. We kind of point it down towards that exhaust manifold. So we take the hot air around that exhaust manifold and we bring that into the carburetor for carburetor heat. Okay? All right. All right, so the carburetor, let's talk about the carburetor. The carburetor is part of the induction system. Where's the other carburetor? The carburetor is part of the induction system, and the way a carburetor works, it's a float type carburetor, is it works on the principle of a venturi, just like we talked about last week. So here's a typical float type carburetor, and it's kind of cut down the middle right here, right? And what you have is the throat. This is the throat, so this is the cylindrical part, and you can see the venturi right there. That's fine. So this is the carburetor that comes off of the Rotax. So it's a little bit different in design in that here's the throat. So this one would be more situated like that. Air would be coming in here. The float bowl is right here, okay? But ours is mounted like this. So the float bowl's on the bottom and the air goes through this way as opposed to that way. But the principle is exactly the same, okay? And I'll kind of go into that a little bit deeper here in a second. So you have a float bowl over here where fuel, a reservoir for fuel. This acts kind of like the bowl on your toilet, right? If you want to flush your toilet, you need some water in there to begin with. So we keep fuel in here all the time so that it's accessible, to the carburetor, and the carburetor can pull from this. As the level of the fuel decreases, this little float, just like the bowl, just like the one in your toilet bowl, moves down. As it moves down to a certain point, it allows more fuel to come in so that we keep that bowl full of fuel all the time, okay? All right, we have a throttle valve. So when you push the throttle in, or a butterfly valve, when you push that throttle in, this little valve is doing this. So when it's wide open, that's when we're going to get a higher manifold pressure, or a higher vacuum pressure. It's actually a vacuum, okay, but don't worry about that. It's reading a vacuum. All right, the faster the air is moving through there, the higher the vacuum would be. That's what it's reading. So when this is wide open, you get a high manifold pressure because we're delivering the maximum amount of fuel and air mixture to the cylinders. Okay? As you pull the throttle out, this closes and it chokes off or it cuts down the amount of fuel air mixture that's going to the cylinders, and the manifold pressure decreases. The suction pressure decreases. Okay? All right. So what is happening in this little cylinder here? What is this? It's a venturi, where we talked about that last week. So what happens in a venturi?
Low pressure, low temp.
Low pressure. So as this air, which is coming from the induction system, comes up through here, around this little discharge nozzle, as it comes around that discharge nozzle, what's happening to the pressure, the speed of the air right here? What's happening to it? It's increasing, and when the fluid increases, what happens to the pressure? It decreases. It pulls a vacuum. It starts to suck. So it starts sucking the fuel. So it's taking fuel from here and it starts sucking the fuel into the airflow, and it mixes that fuel. It atomizes that fuel into the airflow and then delivers that out to the cylinders. In our case over here, air's coming in the carburetor here, it's mixing with the fuel, and then it's delivering it to the cylinders. Okay, where the combustion occurs. All right, so that's the purpose of the carburetor. And we can pass this around and you can see there's the throttle valve, or the throttle valve right there. So that's wide open. That's idle. That's wide open, right? And a carburetor will always have a spring on it so that if the cable were to break, if you're at idle and the cable were to break, your engine goes boom, full power. You don't want a cable breaking and going to idle, right? You'd rather have full power, right? So that's what happens. So you can look in there and you can see the air's coming in this side. And you'll see in this case, you'll see a little cylinder right there that gives us just a little tiny place for air to come through right there. See that? And then you can further choke off or open up the maximum amount or a lower amount. Okay? All right. So rather than have a venturi shape in the cylinder itself, we generate the venturi by, see that thing right there? As that drops down, it chokes it off, chokes it off, chokes it off, which causes the flow of the air to be faster and faster and faster, right? Which would cause a lower pressure, which would suck more fuel. If that were open a little bit more, it would slow down, it would suck less fuel. Does that make sense? Okay, all right. So that's going to be important when I start talking about mixture in just a minute. All right. All right, so I'll pass that around. You guys can kind of look at that, play with that while I'm talking about this a little more. Okay, so that's your carburetor. This is a mixture needle valve, or this is the flow chamber, but this is the needle valve, or air, where's it at? Right here. Where's my mixture needle? Oh, right here, mixture needle. I was looking at the wrong thing. This is my mixture needle. So I could, if I were to take that mixture needle and I were to push it into and kind of choke off the amount of fuel that's going there, right? I would stop the fuel from getting to mixing with the air, right? So why would I want to do that? I would want to do that in order to maintain a consistent ratio of fuel and air. So let's talk about that for just a second. I need these three things for combustion to occur. I need fuel, I need air, and I need a spark. So if I were to take a match and I were to set it on the table right here, okay, the fact that I lit it, that now it becomes self-perpetuating, that's the spark. The wood is the fuel, and the air around it is the air, okay? But if I were to blow on that match, I would put too much air. The ratio would be off and I would blow it out. The fire would go out, okay? If I were creating a spark, if I had a little sparker and I could just create a spark, okay? There's no fuel, it's just sparking, and I were to dump a bucket of gasoline on it, would it explode? Probably not. It's too much fuel. So I got to have the right amount of fuel with the right amount of air and a spark to generate combustion or to generate the fire to keep it going. Okay. Let's talk about the atmosphere. Where do we have the maximum amount of air? At sea level. So the lower we are in the atmosphere, the more air we have. Okay? So if I have, sea level air pressure or molecules of air, and I need a certain amount of fuel to be mixing with it to get the proper ratio of fuel and air, great, I have that. But as soon as I start climbing, what happens to the air? It gets thinner. But I can't change the density of the fuel. So what's going to happen over time? The ratio gets off. Right. So it's too rich. I have too much fuel. So I have to be able to lean the mixture. I have to be able to shut off some of the fuel that's mixing in the carburetor. And the way I do that is I put that little needle valve into that hole and I stop some of the fuel from getting into the air. I do that with this red knob right here. That's my mixture knob. So as I pull that knob out, essentially what I'm doing is I'm choking off the amount of fuel, or I'm leaning the amount of fuel. So as I go up in the atmosphere, as the air gets thinner, I can't deliver the same amount of fuel to it. I have to lean that fuel out. I have to stop some of the fuel, the volume of fuel that's getting in it, because the volume of air decreased. The volume of air has decreased, therefore I have to decrease the volume of fuel, or else my ratio is off. I might still run, but it won't run as good, and I'll get to a point where it won't run at all, right? So we lean it as we go up. That's the purpose for the mixture. I'm maintaining the proper fuel-air mixture. I do that with the mixture knob. Okay, who's got the carburetor? Where's the carburetor? Okay. We don't have a mixture knob on our airplanes. We don't have a mixture knob because our carburetor does it for us. Our carburetor does it for us. We have a pressure sensing carburetor. All right, so that's why I said pay attention to this guy in here. That guy right there. All right, in the top of this, I'm not going to take it off, but in the top of this, there's a little rubber diaphragm. And this little rubber diaphragm, as the ambient pressure of air changes, that diaphragm expands and contracts. And when it expands and contracts, it moves this guy up and down. And when this guy moves up, it's connected to a needle valve that goes right down into the float bowl.
Basically.
It's this needle right here. So as the outside air pressure changes, the needle valve automatically changes to deliver the right, to keep the mixture at the right ratio. That's why we don't have a mixture valve with these carburetors. So it's a pressure sensing carburetor. All right, air pressure sensing carburetor. So it changes the mixture automatically. That's the reason we don't have it. If you're flying anything with a carbureted Lycoming or Continental or something like that, you're going to have a red knob. You're going to have a red knob, and then you must. And for anyone here that's going to fly anything other than a Rotax powered aircraft, you need to know this, because pretty much this is going to be in the air. It's going to be in the cockpit. So you need to know you have to control the mixture of that airplane as you climb and descend. Okay, any questions on that?
When your mixture is off and you're in the air, what's happening other than the engine running off?
What's happening other than the engine running? What do you mean?
So if my mixture is too lean,
Yeah.
and I'm flying,
Yeah.
and I need to change something.
Yeah.
But now what's happening? What am I sensing other than my engine? Like maybe it's sputtering.
Well, you're going to get a drop in RPM or manifold pressure. Okay, and if you're lean, your engine will get hot. Your CHTs will get hot on you. Okay, a rich running engine is so if you throw fuel at it, it cools off. If you take fuel away, it gets hot. So you think about that. If you're running too lean, your engine's going to get hotter. Okay, so there's a balance. When you have a mixture knob, there's a balance that we try and maintain. So in my personal plane, I try and get to cruising altitude, and I try and lean it so that I'm not too hot, but I'm not burning a whole lot of fuel. If I want to run cool, I just run the mixture high, and then I'm burning 8 gallons an hour, or I can bring it back and keep my temperatures where I want, but get down to 6.5, 7 gallons an hour. So it's a game. You can play a little bit with it, right? With a Rotax engine, you don't have that option. You can't You can't do that. It is what it is.
So I guess follow-up question, when my engine is then running hot, what are the consequences there?
Bad. You don't want a hot engine. Yeah, you don't. I'm going to talk about that when I talk. There's a number of reasons that an engine can run hot, and you don't want an engine running hot. And I'm going to get to why you don't want a hot running engine. Okay. And if you have a hot running engine and you have a mixture, put the mixture in. Give it fuel. Give it more. Open this up. Let more fuel get into the mix here, and it'll cool things off. Okay, that's one thing. Okay, so the mixture control. I just kind of talked about that before I got to this slide, but we just talked about that. Let's talk about carburetor icing real quick. Carburetor icing. We have carburetor heat on our airplanes. And if you have, one way to know whether you're flying an airplane that has a carburetor versus fuel injected is if it has a carburetor heat knob or control, you have a carburetor. If you have fuel injected, you're not going to have you don't have carburetor, so you're not going to have a carburetor heat control. Okay, but the purpose for carburetor heat is so that is so that if you do get icing on the carburetor or in the carburetor, you can melt it off. All right. So why would we get icing? Why do we care about icing in a carburetor? No?
Because of the Venturi effect, you dropping the temperature pressure, and it also drops the temperature.
That's exactly right. So the one thing I didn't talk about last week when we talked about air speed increase and pressure drop, what I didn't say is that as pressure drops, so does the temperature. Temperature drops, okay? So who knows what the temperature dew point means? What do I mean by temperature dew point?
Again, the temperature at which the air can hold no more moisture.
Yes. So when the temperature reaches the dew point temperature, whatever moisture which was invisible in a gas form in the air is going to condense. So it's going to become visible. So that might be fog, it might be sweat on the outside of your iced tea glass, that might be dew on the grass in the morning, it might be frost on your windshield, it might turn into snow. Or, you know, what it turns into, what type of visible moisture it turns into depends on the temperature that it drops to. Okay? All right. So what's happening in the carburetor is that as this air is coming in here, especially if it's a highly moisture-laden parcel of air, all right, as it comes through this venturi right here, as it speeds up and its pressure decreases and its temperature drops, we can reach dew point very rapidly. So let's say the dew point, let's say we have high humidity and the dew point's, I don't know, 75 degrees, okay? Well, you can drop the temperature in here to below freezing, just like that. And if that happens, just like that, this doesn't turn to fog, it turns to ice, just like that. And when that happens, it ices up the throat of the carburetor, the butterfly valve, the throttle valve, everything ices up in there, okay? So as it begins to ice up and it chokes off, it's like having a heart attack, your arteries are clogging up here. So as this thing clogs up, the fuel in the air mixture gets choked down and choked down and choked down, and the amount of fuel and air that's going to the cylinders is going down and down and down and down and down. Eventually, not right away, but eventually you'll start to feel the engine start running rough. But that won't be the first indication. What will be the first indication? RPM drop? Manifold pressure drop? Huh? In this case, it probably wouldn't be running hot because the power is decreasing. It could be, but they'd be for other reasons. All right, so if it's a fixed pitch propeller, if you're flying a fixed pitch propeller, your first indication of power loss is going to be RPM. If it's a constant speed propeller, as the power drops off, the blade angle is just going to change to keep the same RPM. You're not going to see it in the RPM. You'll see it in the manifold pressure. So if you're flying a constant speed, an airplane with a constant speed prop, you need to really pay attention to the manifold pressure. That's your power output. That is your power gauge, not the RPM. Okay, so you'll see it on your manifold pressure first if it's a constant speed prop. All right, a lot of people incorrectly think that the temperature needs to be cold. Okay, that's not true. In fact, when I did most of my flying in the Chicago area, when it was in the middle of winter and it was like 10 degrees below zero, I didn't worry about carburetor icing at all. Because the air is so cold, there is no moisture in it. There's just no moisture. I didn't worry about it at all, right? So when do you need to worry about carburetor icing? You need to worry about carburetor icing when it's very humid, okay? And the temperature range is, freezing up to around 70 or so. Actually, here you go. Here's your danger zone. So 80 to 100. So the bigger thing is the humidity. But I mean, it can happen at high temperatures. Okay? All right, so carburetor heat. If you suspect carburetor icing, you need to turn on the carburetor heat. All right, so what do we do? What is carburetor heat? What are we doing with carburetor heat? So it depends on the airplane you're flying. You want to understand, from a system standpoint, where is it coming from? Most piston-driven airplanes provide carburetor heat off of the muffler. All right, so your exhaust system, you have 4 cylinders or 8 cylinders, or however many you got, you typically will run those exhausts. Each cylinder will have an exhaust coming out of it. So here's the exhaust coming out of this one. So this pipe will come out and it will typically go down into a muffler. The muffler is a manifold, right? You got all these going into the muffler, okay? So if you've got 4 cylinders, you've got 4 pipes going into a muffler. And then out of that muffler, we have one pipe, and you see it coming out of the bottom of the cowling on the pilot side. You see that one pipe sticking down, the exhaust pipe? That's coming out of the muffler. All 4 cylinders go into the muffler, then we have one pipe coming out of the muffler. So on that muffler, if you look at the front of the cowl, I'm going to explain what these are in a minute, but there's another little opening down here. You'll see a little opening in the bottom of that cowl. And you'll just see an opening usually until winter, well, it doesn't account on ours, but I'll talk about it in just a second. There's an opening down the bottom of that cowl, and in the wintertime, you'll see a little duct sticking out of that opening, okay? If I turn this sideways and I look at the engine here, engine compartment, okay? So we've got a cylinder, right, and the prop coming out here, okay? The exhaust comes down into a muffler. The muffler then has one pipe coming out the bottom. All right, so exhaust. The other side, you have the other 2 exhausts going in. Okay, air that comes in this little tube from the front, right here, goes to what we call a shroud that goes around the muffler. It's a little aluminum shroud that goes around the muffler. Okay, and we have this on our airplane. This is not where we get carburetor heat from. Most airplanes get carburetor heat from there, so that's why I want to explain it. Air comes in, fresh air comes in and circulates around that muffler, and that muffler can be 800, 900 degrees. So the air that's circulating around that muffler is going to get pretty doggone hot, okay? On most GA airplanes, we then have a method of taking the air, that hot air from here, and here's my carburetors, and pumping it right into the carburetor. So rather than taking the outside air, that outside air that comes in from here on most airplanes, okay, we take it from the muffler, not the exhaust. We don't take exhaust. We don't take the combusted stuff. We take fresh air that comes in contact with the outside of the muffler, and we heat it up through radiation contact, and then we bring that into the carburetor, okay? So essentially what we're doing, if we were doing it that way, when we need carburetor heat, instead of getting outside air coming in here, we duct the hot air off the muffler into here, okay? And that's what melts the ice. If we suspect ice, we just take hot air, instead of bringing it from outside, from here, we duct it from here, and we bring that in instead of in from here. That's what carburetor heat is, okay? We need some method to heat up the air to melt any potential icing that's happening inside the carburetor. Okay, that's not how we do it. How we do it, as I said, somebody asked the question, I think, Michael, you asked the question, where we have the fresh air coming in over here, there's a little box, okay? And then we have another little, it's on this side, but I'll show it over here so you can see. There's a little box here. The fresh air comes in, and when you turn the carburetor heat knob on, you throw a little flap that closes off the air from here and allows the air to come from right off of this little exhaust pipe. It's a little duct that gets up close to the exhaust pipe. So it's not as hot as it would be coming from here, but it's warmer, okay? And then we duct that into the carburetor. That's where we get our carburetor heat from. Okay. So how many of you have flown like Cessnas and stuff like that? You've flown Cessnas. You do the carburetor heat check before you take up on your run up. How much RPM do you lose? Do you remember?
Like 300?
Yeah, you lose like 300 RPM. Okay. So when you're doing your mag check and your engine run up on something like a Lycoming or Continental with a carburetor, when you check the carburetor heat, and you're doing it at about 1700 RPM, where we do ours at 4000. Doing those at 1700 RPM, pull the carb heat on, you might lose 200 or 300 RPM. That's a large percentage of power that you're losing. When you do the carburetor heat check on ours, how much RPM do we lose? 20 RPM? A tiny little amount? Okay, why?
Because it's not as hot.
It's not as hot, number one, and there's another reason. What's happening, first of all, why do we lose RPM?
Your efficiency. Not
Wh-
as good.
Why?
Because the air is warmer.
What's that?
Air density.
It's the air density. It's a mixture. You just change, as soon as you turn on the carburetor heat, you change the mixture. Remember I talked about the ratio of fuel to air? Warm air is less dense. So immediately, as soon as you turn on the carburetor heat, you are immediately running excessively rich. Because you've just thinned out the air, but you did nothing to the fuel. So it's running excessively rich, and you get a drop in RPM. It's not at the right ratio, and the RPM is not as good. You're not getting as much power. Okay. So one of the reasons we get a tiny RPM drop is because the temperature of the air is not as hot. So it's not as thin, okay? But there's also another reason. Remember, this is a pressure sensing carburetor. It senses the pressure difference and it changes the mixture. So it tries to compensate for it. It's a pressure, it tries to keep that from happening. Tries to keep the ratio correct even with the carb heat on, even though you have hot air going in. So that's why we see such a tiny drop for those two reasons. That's specific to a Rotax engine. Okay. Okay, let's look at fuel injected system. If we had a fuel injected system as opposed to a carbureted, and these are pretty popular now. There's a lot of, this is where it's going. Fuel injection system is a much more efficient way of delivering fuel to the cylinders. And so with a fuel injection system, you essentially are replacing the carburetor with a fuel air control unit. So the fuel air control unit kind of takes the place of the carburetor, but you still need these three things. You still got to have fuel, air, and a spark, all right? But now instead of the carburetor controlling the fuel in the air, the fuel air control unit controls the fuel in the air, okay? And the reason that we don't have carburetor icing issues is because we don't have a Venturi carburetor. We don't have that pressure drop happening in a Venturi trying to suck fuel in because the fuel is metered directly from this little spider valve right here, right directly into the cylinders. So the fuel and the air don't pre-mix before they go in. The fuel is delivered separately through the fuel air control unit. Okay? All right. Let's look at superchargers and turbochargers. When we fly what we're flying are called normally aspirated engines. So what that means is we need these things to develop power, right? We need fuel, air, we need spark. As we go up in altitude, what changes? The air. Okay. The air is what we need to aspirate. Aspirate means to breathe. So we have to breathe. So if we have a normally aspirated engine, we have an engine that's breathing whatever the air pressure is, whatever the air is. So you guys ever climb a mountain or ever go up to high altitudes? Is it harder to breathe up there? Okay, so we're normally aspirated, right? So we have a hard time developing power as we go up in altitude because we are normally aspirated human beings. We don't have as much oxygen, as much air, we can't deliver the same amount of power. Engine's the same way. As we go up in altitude, it loses its ability to make power the less and less air we have. So if it's normally aspirated, the higher we go, the less air, the more we have to lean the fuel to keep the right ratio, right? And there's going to be a point where we can't go any higher with a normally aspirated engine. We're going to reach what's called the service ceiling or just the maximum ceiling that we can go to. We're just not going to get any higher than this. All right. The purpose of superchargers and turbochargers is to pressurize this air so that we can go higher. That's the purpose for the superchargers and whatnot. It'd be like us if we're climbing a mountain taking an oxygen bottle. We have supplemental oxygen so that we can get higher. We can develop the same amount of power and go up higher. That's what supercharger and turbocharger does. So all it's doing is essentially the air that's entering the carburetor or entering the cylinder, if it's a fuel injected, that's getting to the engine, getting to the combustion chamber. Okay. As we go up, the molecules spread out and spread out and spread out. Therefore, we have to decrease the fuel to keep the ratio right. But if we had a way to, as we go up, to compress that air, now we can deliver, let's say, sea level pressure at higher altitudes, and we can maintain power up to a higher altitude. That's what a supercharger and turbochargers do. The only difference between these, there we go, is that a supercharger is an engine-driven air pump or compressor, basically, okay? So the engine is driving the compressor wheel that's compressing the air. So the disadvantage to that is that if I have, I don't know, a 300 horsepower engine, I'm using some of that horsepower to drive this motor to compress the air, okay? I'm getting the same result, I'm getting compressed air, but I'm having to use some of my engine power to do it. A turbocharger doesn't use a turbocharger doesn't use it, it uses the exhaust. So here's how that works. So here you have your intake manifold going in, this is a 6-cylinder engine. You have your exhaust manifold, okay? And here's your compressor right here. So the way a turbocharger works is, since these engines are discharging spent fuel and air anyway, normally we would just dump this overboard, but with a turbocharger, we have a wastegate here where we can say, hey, if I don't want to engage this, I'll just open this right up and let all of this just dump overboard. But if I need to spin this wheel, I can close that off and force this to spin the wheel before it dumps overboard. And by spinning the wheel, I'm compressing the air that's coming in, I'm compressing it so I get higher pressure air going into the cylinders so I can develop higher power. Does that make sense? How that works? So I've got to have a means of pressurizing the air. If the molecules are spread this far apart, I can't develop a lot of power, but if I can get the molecules tight together, like down at sea level, I can develop a lot of power. Yes?
So the supercharger, the engine-driven compressor.
The supercharger, this little compressor is driven by the engine. Turbocharger, it's driven by exhaust gas. So I'm not taking any power away from the engine to drive the fan, to drive the compressor motor. Okay, so that's the advantage of a turbocharger. The thing you need to be aware of, be careful of, because there's a lot of planes, GA airplanes, that have turbochargers. Okay, be careful and know whether you have an automatic wastegate or not. Okay, if you don't have an automatic wastegate, you have to be very careful at lower altitudes. You can put too much power into these cylinders, you can blow the head right off. You can literally put so much power in here that the head blows off of the cylinder, right? So you got to be very, very careful about if you have a supercharged or turbocharged engine. You have to be careful about watching manifold pressure. Because now we're looking at the pressure, and in this case, the manifold pressure gauge would be right here. It'd be just on the downstream side of the air flow intake, right? So if these cylinders are designed to take, X amount of pressure and you bump it up too far, you could blow the head right off. So you got to be really careful and watch manifold pressure on these types of engines. If it has an automatic wastegate, well, then the wastegate's designed to open before you end up with too much pressure here. It'll open up and decrease the amount of power amount of manifold pressure going to the engines. But if you don't, I used to fly a plane that it had a turbocharger, but it didn't have an automatic wastegate. And there was a big red light about a $50 size right in my sight. And if the manifold pressure got too high, bam, that thing was bright, it would light up, so I would pull the power back. So you gotta watch that. Okay. Questions on that? You understand why supercharger, turbocharger, what they're used for? Okay, so normally aspirated engine maybe gets up to 14,000, 15,000 feet, something like that. You get a turbocharger, supercharger, you can get up into the flight levels. Piston-driven airplanes, you can get up into the mid-20s, maybe the high 20s. You want to get higher than that, now you need a jet engine. The jet engine is a compressor, so that's compressing the air right there. Okay. All right, let's look at the ignition system. The ignition system is the spark. That's the spark side. That's what's igniting the fuel-air mixture. Somebody asked a question about ignition. Yes, right? What was your question again?
It was, how do the sparks know exactly?
Exactly. How are they? It's called timing. Okay, that's called the timing. So if you ever heard somebody talking about their engine, and maybe they went to a mechanic, the mechanic said your timing is off, your timing belt's off, or your timing is off. Okay, so what they're talking about is, when is the spark plug firing? Is it firing at the right time? Okay, and it's all about, where is the piston at in the travel. So let me draw it over here. Okay, so let's say, I'll get out of the way here in a second. Let's say that's my cylinder. There's my head, and here's the piston in the head, and I'll just draw it straight down for now. Okay, and you've got a spark plug coming in here, and you've got a spark plug coming in there, let's say, okay? So what's happening is, we need this piston to go up, intake, compression, power, exhaust, right? All right. The point in time where we want these spark plugs to fire is not when the piston is at top dead center. We don't want the piston at top dead center. We want the piston to be before we get to top dead center. The reason is, we want the momentum of the piston to be going up while the explosion happens, so that as the gases are expanding, this is forcing it up and you get more of a power stroke out of it. If you get right to the top and it's starting to come down and it fires, you're not going to get as much power. But if the momentum is moving up and then it fires, and the air and the fuel and air is trying to expand and the piston is moving into it, now it really gets a recoil and goes, right? So the timing has to do with how many degrees before top dead center do the spark plugs fire. And that'll depend on the engine. But you'll hear like 25 degrees before top dead center or something like that. What they're talking about is the angle of the arm right here, the angle of the crankshaft. Where's the angle of the crankshaft before when it's top dead center? When the piston's top dead center, the piston arm is straight up and down on the crankshaft, right? When the piston's down here a little bit, this is going to be a little crooked. It's not quite straight up and down yet. Okay? So when you're whatever number of degrees it needs to be before top dead center, that's the timing. That's when the spark plug is supposed to fire. Okay? That's what it means by timing. All right. So there's with ignition systems in airplanes, we have something called magnetos. All right? Who knows what a magneto is? What's a magneto?
It's a separate engine that provides a charge to the spark plugs.
It's an electrical device. Yeah, it's an electrical motor, essentially. So you can have magnetos that are attached to the engine, so that when the engine is turning, It's turning the little magneto, and as the magneto turns, it generates the spark that goes through the spark plug wires and goes to the two spark plugs. All right. The reason we have two of them is for redundancy and for efficiency. So if you have two spark plugs as opposed to one, like your car probably has, if you have two spark plugs, when the fuel air mixture is burned, it burns more evenly across the face of the piston, and you get a better power stroke out of it. Okay, if you only have one, it's still going to fire, but it's not going to be as powerful. It's not going to be as efficient than if you have two. Okay, so efficiency is one reason to have both a left and a right magneto. And what I mean by both a left and a right magneto is I have two spark plugs. One of them is the left ignition, one of them is the right ignition. Okay? So one of the magnetos fires one of the spark plugs, the other magneto fires the other spark plug. So when you do your engine run up and you do the mag check, you go from both to right to both to left to both. All right, what you're doing is you're turning off one of the spark plugs in each cylinder. So we get a drop in RPM simply because the engine doesn't quit, but we get a drop in RPM because we're only firing on one spark plug. So it's not as efficient. It's not creating as efficient of an explosion. You're not getting as much power. So you lose a little bit of power. That's how we test to make sure both sides are working. Turn one off, you lose RPM. Because now on a 4-cylinder engine, if they're both on a 4-cylinder engine, we have 8 spark plugs firing. When you turn one of the ignitions off, you only have 4 spark plugs firing. And then you turn the other side off to check the other. Does that make sense? Okay. All right, so that's the ignition system, and it's a self-contained system. In other words, it's electric, but it's self-contained in that if you turn off the master switch, the engine still runs. The engine doesn't quit when you turn off the master switch. Okay? Once the engine is running, once the engine is turning, if you have mechanical mags that are attached to the back of the engine, once the engine is turning, the magnetos are spinning. So as long as the engine keeps running, the magnetos keep spinning, and it's kind of a self-contained thing. Okay? The Rotax is a little bit different, so I want to talk about that. The Rotax does have magnetos, but rather than having 2 mechanical magnetos, we have 2 electronic mags. That's these 2 boxes right up here on top. Okay? And we call them A and B, but left, right, A, B, whatever you want to call it, doesn't matter. There's 2 of them. Okay? And these control the firing order. These control the timing on when the spark plugs fire. They get their electrical input from the motor right here. On the back of the motor, on the flywheel right here, is a generator. So as long as the engine is turning, see that flywheel turning? As long as the engine is turning, then that generator is generating power. As long as we're generating power, these 2 boxes have the power to fire the spark plugs. So the same thing occurs. Even though it's electrical, if you turn off the master switch, as long as the engine's turning, everything keeps firing. Okay? I don't know why I didn't put 4 castering wheels on this thing. That was a mistake on my part. All right.
You know, it's probably good for everyone to know that, you know, you're running, you park your plane, we're shutting it down, so you can just put the key on.
Yes, okay.
But
So
you're killing your magneto.
yes, that's exactly right. So let's talk about that real quick. So if you're flying an airplane, I erased this. If you're flying an airplane that has mixture control, how do we shut it off? For those of you that have flown a Cessna, how'd you shut the Cessna off? You take the mixture knob and you pull it all the way out. You starve the engine. So you take away this and the engine quits. You lean it completely and the engine quits. We don't have the ability in a Rotax to lean it. So how do we turn it off? We turn the key off. So what we're doing is we're turning this off. So in an engine that has a mixture control, you turn this off. In ours, we turn this off. We got to get rid of something, right? To shut the engine off.
So there's potential to start it when we purchase another?
Yes. So that's the thing that you want to be aware of. Be careful whenever you turn a propeller. Understand that with magnetos, when this propeller turns, when this is happening, the magneto is turning. Magneto is turning, and when the magneto is turning, you are getting a potential spark to the cylinder. And if there's any residual fuel in that cylinder, that engine can start. Okay? So when you're out there propping that plane, or when you're out there burping the engine, what should we be aware of?
The dark thing.
That engine could start. All right, so here, be very careful about this. Before you touch that propeller, you look inside and you make sure the key is in off position and the key is out. The throttle's all the way back, pulled to idle, and the chocks are on. And the brake is on. Okay? And then when you prop it, when you burp it, you don't do this and put your head in the arc of the propeller. You stay away from the propeller and you burp it like this. Okay? All right. You will, if you haven't already, until these Rotax become more popular in the United. They're popular everywhere else in the world, except for in the United States. They're becoming more popular now. When you go out there and you start burping the engine, it's not uncommon for someone to come running up to you and say, "What are you doing? You should never turn a propeller. Never do that. It's dangerous." All right? And they're right with most other engines. They're absolutely correct. Okay? The reason is there's something called P-leads that tie into the ignition module here, or to the magneto. And if the P-leads are broken, then you have a hot mag. And turning that mag means it's producing a spark. Okay? So and you don't know whether you have a hot mag. If that thing broke the last flight, you don't know, and you go out there and you turn the prop and the engine could start. All right? You don't need both magnetos operating for the engine to start. It'll start on one mag, right? It'll start with one spark plug. Okay, so all you need is one broken P-lead and the engine could start on you. Okay. The reason it's especially dangerous with most engines is that most engines are shut down how? What do we turn off? So we're not testing whether the spark is working or not. We're just shutting the fuel off. Every time we turn one of our engines off, we're verifying that the P-lead's not broken. Because if the P-lead was broken, you turn the engine off, pull the key out. I mean, you turn the key off, pull the key out, and the engine would still be running. So every time we turn a Rotax engine off, every time you turn any engine off by shutting off the spark, you're testing the P-lead. Okay, does that make sense? So if you own, somebody was going to buy an airplane. If you own your own airplane and it has mixture control and mags, every now and again, rather than you should still shut down with the mixture, but every now and again, turn the key off real quick and then turn it back on. You'll turn it off, you'll hear the engine start to stop, and then you turn it back on, and then you start it with fuel. The reason we start it with fuel kind of goes to this. If you start it with fuel, that means that there should be no fuel in the cylinders. So if you are turning the prop, there's nothing in there in case your P-lead is broken. Does that make sense? Okay. All right, so here's kind of an overview schematic of it. So you got your two magnetos. One of the magnetos operates, one spark plug in each cylinder. The other operates one spark plug in the other cylinders. If you have a key, not all airplanes have key switches. Some will just have mag switches. So my personal plane just has two. I got a mag button, a mag switch, and a mag switch, and a starter button. So rather than a key, I just have to make sure my mag switches are turned off. Right? If I want to start it, I just turn those on and hit the start button.
They basically work the same way.
It's the same thing.
Grounding out.
It's the same thing. Yep. Right. Okay. All right. Let's take a break, another 5-minute break, and then we'll go on. Okay. Oil system. So oil. Was it too loud? It just gets pretty hot if I close it. Okay, so a couple of purposes to have oil in the engine. Obvious is lubrication. It also cools the engine by removing heat from the cylinders and the moving parts. Provides a seal between the cylinder wall and the piston, so when that piston's moving up and down the cylinder, it's actually not touching the sides, or it's not supposed to be touching the sides. That oil creates a hydraulic seal or place where it kind of moves right up and down there. And then it's carrying away contaminants, so that's the purpose for the oil system. So we have, most aircraft engines will have something like this. Most of them are what we call wet sump systems. So in a wet sump system, just like in your car, the oil is in the bottom of the crankcase. So when you change the oil of your car, or when you take it to an oil change place, you drive over a little pit and the guy's underneath, right? You down the bottom of the oil, bottom of the engine, takes the drain plug out. So in most aircraft, it's what is called a wet sump system. It's a dry sump system in the road tax. I'll get to that in a second. You're going to have somewhere, you'll have an oil temperature gauge and oil pressure gauge from a monitoring standpoint. You'll at least have that. Okay, you got to have that. You need to know what your temperature and your pressure are. Oil temperature is important, not nearly as important as cylinder head temperature, which I'll get to in a minute. Oil pressure is very important. If you don't have oil pressure, that means the oil's not moving around and lubricating and doing the job it's supposed to do. And if you lose oil pressure with a running engine, the engine will seize pretty quickly. It will seize, and I mean, it'll weld itself together and stop and be ruined. Okay? So oil pressure is important. Keep an eye on oil pressure. In fact, what's the first thing on the checklist after you start the engine? Oil pressure. Make sure you got oil pressure. If you don't have oil pressure, turn it off, like quickly, right? Because it's going to seize pretty fast. So that's really important. Make sure you have oil pressure. You'll have, most airplanes now have a filter somewhere in the line. Some of them have oil coolers as well. Some of them don't. Some of them just have screens, believe it or not. Just have an oil screen, which is ridiculous. But ours have oil filters on it. And ours has an oil cooler. So the oil cooler on ours is right here. Right here. Actually, I drew these in the wrong, kind of the wrong way. The smaller ones up here, the bigger ones down here. But that's the oil cooler right there. That thing right below the spinner. Looks like a radiator. Everybody know what a radiator is? Okay. All right, so the oil cooler is just a radiator. It's got oil running through it. Call it an oil cooler. Okay. All right. Our aircraft, the Rotax engine, does not have a wet sump. It has a dry sump. So here's the Rotax setup. If we had a wet sump, then on the bottom of the crankcase we'd have a tank down here that the oil sat in. And when you have the oil in the bottom of the crankcase, as the crankshaft is spinning and everything's moving, that's slinging oil. Plus you have pumps, pressure pumps moving things around. All right, and when you turn the engine off, the oil just drains right back down into the bottom of the crankcase. Ours doesn't have that. We have a separate tank over here. And when you check the oil, you check it on this little separate tank. One way to know that you have a dry sump versus a wet sump is the length of the dipstick. Our dipstick is this long. It's a little tiny, it's that long, it's a little tiny dipstick. If you check the oil in your car, it's a dipstick that's that long, right? Because you have to get it from the top of the engine all the way down to the bottom of the crankcase, to the oil pan, in order to check the oil. So it's going to be a long dipstick. If you got a little tiny one like this, you pretty well know it's a dry sump system. The oil's kept outside the engine. All right, so the oil, in this one we have the oil cooler is here, got an oil pump here, and the oil filter is, you can see it right here. See if I have this. So here's the oil pump right here, here's the oil filter right here, tank sits over here, and then there's lines going all over the place, but that's the pump, the filter, and then the tank is sitting over here, and the oil cooler is sitting down. All right, we take about 3 quarts of oil. About 3 quarts of oil. So if you're low on oil, don't put a quart in, because you'll overfill it. Okay? How do we know we have enough oil? On the dipstick. Dipstick looks, got a little flat section like that. And the ring on the top of it. So as long as the oil is somewhere in that little flat section right there, then we know we have enough oil for operation. Okay? If the oil is just maybe slightly low, if it's right down here somewhere, okay, burp it again, or burp it a few times just to make sure you can get as much oil back in there as you can. Okay? If it's right, and if it's just a little bit low and you want to add some oil, like I said, don't add a whole quart or you overfill it. Just add 200 or 300 milliliters at a time, and then recheck. if the oil is right here, let's say it's just right at the bottom of the flat. It's right there at the bottom of the flat, but it's on the flat. Is it okay to fly? Okay? All right, so it is okay to fly, but you want to ask yourself, what am I doing, right? If you're just going to stay local, you're in the pattern, you're not really treating the engine harshly, it's probably okay. If you're going to go on a long cross country someplace, I'd put oil in it, right? So just kind of use common sense.
So do you not burn the engine in a wet sump?
You don't burn the engine in the wet sump, you don't have to. All right, so let's talk about why that is. If my oil tank was sitting down here on the bottom of the crankcase behind the oil pump, say my oil tank was down here, that's where my oil's set. As soon as I turn the engine off, all of the oil is inside here, right? Except maybe some running through the oil cooler, but the oil's inside here. So as soon as I shut off the engine, where's the oil go? Right down into this little tank, or to the oil sump, right? And I would have a dipstick that probably went from up here all the way down into there. So when I shut the engine off, the oil drains down to the bottom, and as long as I give it a few minutes to drain down, I can check the level like you do in your car. With this type of a system, you've got oil in the tank, you've got oil in the lines, you've got oil in the engine, you've got oil in the filter, in the pump, all over the place, some in here. So when you shut the engine off, and this pump stops moving the oil, where's the oil go? Stays right where it's at. So now when you check the oil level, you have no idea whether you have enough oil in the system to safely operate the engine. So we have to burp the engine, and by burping the engine, what we're doing is we're moving the oil that is in the lines and in the engine, or as much of it as we can. We can't get it all, but we're going to move as much as we can from here back to here so that we can properly check the level. All right? And the way it works is we're developing crankcase pressure. Does somebody have their hand up? We're developing crankcase pressure. And we do it with the cylinder. So, without getting too technical, there are rings that run around this cylinder. They're called oil rings and scraper rings. And there's little gaps. It's not completely sealed. But when this piston is moving up and down the cylinder, there's little, it's not completely sealed off. Air can escape down there. Now, when the engine's running and it's going so fast, the air is not really escaping, okay? But if you slowly move the propeller and you get the piston to come up and down and kind of slow, like in about this fast, that's about when we're burping the engine, okay? If you get to the compression point where both the cylinders are closed, I mean both the valves are closed, and the piston comes all the way to the top, you're developing a lot of pressure, you're compressing the air in there, right? Well, that compressed air sneaks back around the cylinder back into the crankcase and pressurizes the crankcase. And we build up pressure in the crankcase and we move the oil back. That's why we burp it. So when you're spinning the propeller and you reach the heart, you can feel it get to compression, just kind of go slow, kind of slowly go through compression. So as you're getting to compression, just kind of slowly work through compression, and the air is escaping back around the piston, back into the crankcase, pressurizing the crankcase, and moving the oil back to the tank. That's how we burp it. It's called blow-by. It's blow-by for this piston. Okay. That's why it's critically important. You have to burp the engine on a Rotex, or you don't know how much oil you have. Okay. All right. Cooling system. So oil is part of the cooling system, but we also have in most GA airplanes are simply air cooled. So if you look at this cylinder, and where's the hottest part of the engine going to be? Anybody have any idea? Where the explosion happens.
Combustion chamber.
What's that?
Combustion chamber.
The combustion chamber, where the explosion happens. Right there. Right at the top. Right where the piston gets up there and the explosion happens right there. So the head, this thing right here, is the hottest part of the engine. Okay? So we talk a lot about cylinder head temperature, CHT. I said oil temperature is important. It is. This is more important. Cylinder head temperature is more important. So when we talk about engine overheating, you don't want this overheating. Okay? This overheats, bad things start happening. Okay? So we have to watch the cylinder head temperature. Most GA airplanes if you look at this, if you look at the barrel of the cylinder, you see these fins, those are cooling fins. What those cooling fins do is it increases the area of aluminum, in this case it's an aluminum barrel. It increases the air surface area so that as air moves past it, it can dissipate, it can take the heat away from the cylinder barrel. If I just had the barrel without the fins, if I blow air across the hot barrel, it's still going to cool it, but not nearly as much as if I give it some surface area to come in contact with the air to come in contact with to dissipate that heat. That make sense? All right. Most aircraft engines, when you look at the combination of the barrel and the head, you would see fins all the way to the top. If you see fins all the way to the top, the entire thing, the barrel and the head, are air cooled. You notice this one, the hottest part of the engine doesn't have cooling fins on it because these engines are liquid cooled. The head, and only the head, is liquid cooled. So we run radiator fluid basically through a jacket around this head to keep the head cool. Only on Rotax, well, on Rotax engines. I won't say on Rotax. Okay? All right, so from a cooling standpoint, generally what's going to happen is you just got air coming in these openings in the cowlings on most planes. You've got the air coming in and circulating around these cylinders with those baffles on it and dissipating heat, pulling heat off those cylinders, and then we dump it out the pod, usually through cow flaps. Okay, usually fixed cow flaps, but if you have a high performance, high powered engine, you can have movable cow flaps where you can open that up so that you get more volume of air through there to help cool the engine a little bit. Right? So we do have air cooling happening, but we also have liquid cooling happening on the Rotax. So here's the coolant system for the Rotax. So here we're looking at the side of the engine. Here's the gearbox, the prop flange right here. These two cylinders. You have basically a little reservoir right up on top here, and you can see on this, it's got the radiator cap on it, just like the car does. Anyway, you can look at it. Little radiator cap right there. So that's where we keep the coolant, and then the coolant flows into the heads only. Only goes into the heads. Circulates around the heads. The pump, the coolant pump is on the back down here. So we're pumping that liquid through the heads, through a radiator, just like you have on your car. And this one, the bigger one down here, is the coolant radiator on the front of the Rotax, on the front of the Remos. Okay? It's a closed loop system. In other words, it's not getting any outside influence in it. There's no air or nothing else coming into it. So there's no filters in it. It doesn't need a filter like an oil system would or like an air intake would, which is open to the outside world, if you will. It's a closed loop system. So we don't really, in theory, need to do anything with it, except every 6 to 8 months or so we flush the coolant and replace the coolant, just for, coolant breaks down after it gets too hot for too long. Okay, exhaust system. So we got to do something with the spent gases. So we have the fuel air mixture going in the cylinders, we explode it, and we got to exhaust it out. We got to do something with it. Typically, that's pretty simple. We've kind of talked about it already. We've got exhaust pipes coming out of each cylinder. It goes into a muffler, usually, and then one pipe coming out of that. Sometimes you'll see a straight exhaust. You've seen some old World War II fires that have just the exhaust pipes coming out the side. They're loud and awesome. Yeah, those don't have mufflers. They're just cool and loud. All right. Starting system. All right, the starting system consists of a starter. Can you spin that around to show the starter? Unless at some point put a forecast. Here's your starter right here on the back of this thing. Okay. What we need for a starter, and the reason we have a starter, we can start the engine without a starter. We just have to have somebody in the front moving the prop. Okay. If you move the prop and the magnetos are hot and there's fuel in the cylinder and you move the prop, what's going to happen? It's going to start, right? So you can prop, we call it propping the airplane. You could prop an airplane and get it to start. And that's the way it used to be done, right? But we got tired of that, so we decided to put a starter motor on there so that we didn't have to go out there and do it. We just do it with the key from inside the cabin. But then that requires us to put a battery in the airplane. So that's how we started getting batteries. So the battery is there to supply power to the starter so you can start the engine. Okay. A starter is just a little gear that engages with the engine and spins the engine. When the engine's spinning, that starter spins the engine spins the magneto sends a spark, and then it goes. And once it's going, it's self-contained. Okay. This is kind of the schematic of it. Basically, you've got a starter motor, which is what we show on the side here. You got a battery supplying power to it. Your ignition switch, starter contactor. You don't have to know too much of that, but just understand that unlike your car, which is totally electronic ignition, if you start your car and you take the battery out, the engine quits. If you start an aircraft engine, you take the battery out, it just keeps on going. The only thing we need a battery for in an airplane is to start it. So that's what we use it for.
All manual transmissions.
Yeah, it used to be like that way in cars too. Yeah, you could pop the clutch and let it go. I had a car that I had to do that with all the time. All right, let's talk about combustion. So now we're going to get into this area that you were talking about, hot, getting the engine hot. All right. So we have normal combustion, we have abnormal combustion. Can you find the piston in there that was abnormally combusted? That detonated. Normal combustion, what's occurring is when you have that power stroke, you're getting a nice even burning, and that piston is just evenly being pushed down, pushed down, pushed down, pushed down. Abnormal combustion is more like taking a hammer and smacking the top of the piston. That's abnormal combustion. So rather than a nice even burning, you're getting a hammering type explosion that's going on inside. I mean, this is an explosion too, but it's an even combustion type explosion. All right. What can happen, or what does happen when that occurs, is overheating, or what can cause it, I should say, is overheating of the cylinder head. There's generally two things: pre-ignition and detonation. So detonation occurs when the temperature in the cylinder gets too hot, right? Detonation. Yeah, detonation occurs when the temperature gets too hot. Rather than getting an even burning of the fuel air mixture, you get an explosion that happens. And so now you get that hammering effect. Okay. Have you ever driven a car where you hear a knock, 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 knock in the engine? That's detonation. What you're hearing is detonation. So your cylinder heads are getting too hot. You're detonating inside the cylinder. You don't hear that in an airplane because there's a lot of other noise and things going on. You hear it in a car, you don't hear it in an airplane. But that's what's happening. All right, so there's a number of ways that you can get detonation, or that you can get, I should say detonation, you can get cylinder head temperatures too high. It's having too high a cylinder head temperature that causes detonation. You can use the wrong fuel grade. So the octane rating on the fuel, you never ever want to go lower octane. If the fuel that you want isn't available, go to the next higher octane rating. Never go down. All right? So what do we need? What's the minimum octane rating in these airplanes? In this engine? 91. 91 unleaded in these engines. What do all airports sell? 100. We can use 100. Some airports sell 87. You can't use 87. The lower the octane reading, the hotter it burns. The hotter it burns, the higher your cylinder head temperature, the more you're likely to get detonation to occur. Okay. Operating an engine with too high a manifold pressure. Remember, I was talking about if you have a turbocharged or supercharged engine and you're running it at sea level, already high pressures, and you activate, you let that cylinder, you let that. You let that cylinder pressure build up. You get too much heat inside there, and that can raise cylinder head temperatures. Lean mixture. The leaner the mixture, the hotter the cylinder is going to get. Yeah. The leaner the mixture, the hotter the cylinder is going to get. Staying on the ground, extended ground operation or steep climbs where you can't cool the engine properly. So when we're climbing out, what are we always watching? Cylinder head temperature. We're watching the cylinder head temperature, right? Okay. So when they get too hot, you can start getting an explosion in the cylinder as opposed to a nice even burning. That's called detonation. Okay. The other type of bad thing that can happen is called pre-ignition. Avoiding detonation is going to be the opposite of basically what I just said. Don't use the wrong fuel grades. Lower the nose. If you're climbing and getting too high CHT, what do? Lower the nose a little bit. You're going to get better airflow, better cooling. Enriching the mixture if you need to, if you can. If you have a way to do that, enriching the mixture. If you have cowl flaps, open the cowl flaps, get more airflow going through there. Reduce the throttle setting a little bit. Right? Do anything and everything you can to start reducing your engine, your CHT temperatures if they start getting too hot. Okay. All right, pre-ignition. This one's really, let me show you, by the way, an example of, that's a good cylinder. That's one that was detonated too much. Okay? You can get such bad detonation and pre-ignition that you actually end up with a hole in the cylinder that actually burns a hole right through the cylinder. Okay? Somewhere I've got one where the cylinders are basically, well, this one, I'll pass this around, you can see it melted. It melted the rings, welded the rings in place. Yeah. Okay, pre-ignition. Here's what's happening with pre-ignition. Remember what I said ignition was, the timing? It's when do the spark plugs fire. So we want the spark plug, so here's the top of the cylinder. We don't want the piston to get right here before it fires. We want it like right here somewhere so that the momentum carries it up and I get a good spring back down, right? So if I want the spark plugs to fire when I'm right here, think about this crankshaft, this connecting arm connected to the crankshaft here, right? I want this to get all the way up and around, and up and around, right? What if it fired way down here, and I don't have the momentum to go this way, and it wants to force the crankshaft to go the opposite direction? Can you think about the torsional stresses on the crankshaft? That's pre-ignition. What's happening now is instead of the piston getting up to here so that when the fire happens, I've got the momentum to carry through, it happens down here and it wants to stop it. The amount of catastrophic, you can have catastrophic failure and rapidly, you can get catastrophic failure. So high CHTs can lead to detonation, which can lead to pre-ignition and catastrophic failure pretty quickly. CHTs are incredibly important, way more important than oil temperature. Okay? All right. All right, let's talk about fuel systems. The most important thing to understand about fuel systems is the entire fuel system on the airplane that you're flying. Most engine failures, and I mean like 90%, are fuel starvation. Most of them. Engines quit on airplanes because they run out of fuel. And that doesn't mean that there's no fuel in the airplane. It just means there's no fuel in the engine. Most of the time, not maybe, I won't say most of the time, but a lot of the time, there's fuel in the airplane, but the pilot didn't understand or something happened with the systems. They were unable to get the fuel from the tank or tanks to the engine because they maybe did not completely understand the system, the fuel system in the airplane. So they crash land the airplane because they don't know how to get the fuel to the engine. Don't ever let that happen to you. You need to understand the systems on your airplane. I'm going to talk about really simple systems because most GA airplanes are pretty simple. You typically have two kinds. You're going to have a gravity-fed system or you're going to have a fuel pump system. Most high-wing airplanes will be somewhat gravity-fed. All low-wing airplanes are going to be fuel pump, right? If you have fuel in the wings above where the carburetor, if the carburetor is down here, where do I got to get the fuel to? I got to get the fuel to the carburetor. I got to get the fuel, there's the fuel line coming in. So I got to get the fuel to this point right here. All right? Well, if the hose from the fuel tank, the outlet from the fuel tank is up here, Well, it's gonna flow downhill, and I've got pressure to get the fuel down to the carburetor. But if the fuel tank's down here and the carburetor's up here, I need a pump to pump it uphill. Pretty simple, right? So just think about where the fuel tank is versus where the carburetor or the fuel control valve unit is, and that's where you gotta get the fuel to. So you either got gravity fed or you got a system that requires pumps. Even if you have a gravity fed system, a lot of times they'll have pumps associated with it. Okay. So do we have a gravity fed system in these airplanes or a fuel pump system? It's a fuel pump. Even though we have high wing, we don't have fuel in the wing. We have fuel behind the seat. All right. Okay. Look familiar? All right. So here's the engine. Here's the carburetor. I got to get the fuel right there. The fuel tank is behind the passenger seat, and it's shaped kind of like this. Here's the fuel tank, fuel in it. And the hose out of the bottom of the fuel tank is right about here. So I've got to get it uphill to there. So I got to have a fuel pump. Okay? So we have two fuel pumps on this engine. We have a mechanical pump and we have an electric pump. The mechanical pump is right here. That's the mechanical pump right there. So when the engine is turning, this is connected to the gearbox, the prop gearbox. So as long as the engine is turning, that little pump is providing fuel or is pumping fuel into the carburetors. But when we start the engine, that pump's not turning. So we have an electric fuel pump to provide fuel pressure during the start. And then after we start, we turn that fuel pump off. Right? And then we leave that fuel pump off until when? Until takeoff. And then after takeoff, what do we do? Huh? You leave it on. We leave it on. Why do we leave it on? Anybody know? The instructor told you why? Here's why. We're running fuel that has ethanol in it. Ethanol is more susceptible to vapor lock. So we leave the fuel pump on. So we're actually running on we have two fuel pumps, so we have higher fuel pressure all the time to counteract any potential vapor lock that could be occurring in the system. That's the reason we leave it on. But if we're going to leave it on all the time, why do we turn it off after start? Why not just leave it on? We're testing the mechanical one. If we started with the mechanical one, we don't know whether this one's running by turning it off between the time we start and the time before we take off. If this one's not running, the engine's going to quit before we make it to the runway. And now we know this pump's not working. That's why we turn it. Okay. Our system is really simple. We have one tank and we have one valve. Everybody know where the fuel valve is? Fuel shot valve is? Who doesn't know where if you're training already? If you've already been in our planes? It's right in the front. Right in the front. Right on the center console. Right there. Okay. It's either on or off. Either on or off. Okay. If you're flying planes that have multiple tanks and more complicated fuel systems, you can have varying methods of moving fuel from this tank or that tank or both tanks, or tanks to header tanks. There's fuel systems can get complicated. Okay? So it is your responsibility to absolutely, completely understand the fuel system and how you move fuel from the tank or tanks to the engine. And there needs to be no, like a zero gray area on how that happens in the plane that you're flying, like zero gray area on how that happens.
Question.
Yeah.
I mean, theoretically, I can understand why you use ethanol gas. It's cheaper.
Well, that's all I can really get around here. It's not cheaper, it's more expensive. Ethanol's more expensive.
Yeah, but they have gas.
Oh, it's cheaper than, well, you're asking why I use it. Yeah, but it's unleaded. I'm using unleaded because it's cheaper. Yeah. I'd rather find unleaded with no ethanol, but it's hard to find.
It's very low.
Yeah.
But avgas does not have ethanol.
No, avgas has no ethanol.
Does it have a certain amount of lead in it?
It does. It's a low lead content. That's what I call it, 100 low lead. Yeah. Okay. show you this. This isn't as pertinent anymore, but it's still in the book, so it could still be on the test. That's hard to see, but this is figure 732 and 808325. But basically, these are different fuel gray octane grades and colors. So in aviation fuel, we put a dye in the fuel, so that when you're testing the fuel, you can look at the color of the fuel, and if you see red, you know you have 80 octane. If you see green, you have 100 full lead. Blue is 100 low lead. Clear or straw color is jet fuel. Okay. Now the fuel that we put in our airplanes is clear or straw color because we're not using aviation grade fuel. We're getting it from Buc-ee's. Okay. All right. So it's going to be clear. So what do we do when we test? You know, we have this little sump. We have this little tube sticking out the bottom. Everybody's familiar with this, right? It sticks out the bottom of the plane right there. That's the sump. That's where we check the fuel. And that sump, what it does is, once the fuel level gets below this pickup line, we can't get any more fuel to the engine. So when the engine quits, we still have fuel in the plane. We have about 1 gallon right there. That's called unusable fuel. 1 gallon of unusable fuel. This is 21 gallons of usable fuel. Okay, so total, the tank holds 22, but we can only access 21 of it because a gallon of it's below that point. So down here we call this the sump. So if there's any contaminants or water or crap in the fuel, it's all going to drain down to this sump. And that's why we test it right there. We pull some fuel out of that low spot, and if we see dirt or water or junk, we dump it out and we keep draining until we get all that out before we go fly. When we test it with this clear plastic little tube, and the reason it's a clear plastic little tube is because we want to see the color. We want to see what the color is. Okay? Generally speaking, you can't find this, and you can't find that pretty much anymore. Pretty much all you see at airports is 100 low lead or jet fuel. Pretty much all
Yeah, do I understand correctly, jet fuel has kind of like a diesel and smell?
Jet fuel smells like kerosene.
Kerosene.
Yes, diesel. Yeah. Yeah, it smells like kerosene. So when you check your fuel, you're looking at the color, you're looking for contaminants, you're smelling it to make sure if it's a straw color, which is what ours is, you're smelling it to make sure it smells like gasoline and not kerosene, right? Not as susceptible to we're not as worried about it here because we fuel our own planes, you know what I mean? I'm not as worried about it. You still want to do it, get in the habit of doing it.
So when we go cross country, we got to get
If you have to get fuel, you're going to get 100 low lead because nobody's going to have unleaded.
What does kerosene smell like?
Yeah, like oil. Yeah.
Diesel, it's diesel.
Yeah, it's diesel fuel, and it's also very greasy feeling. Like if it's gasoline, if it's pump gas, that'll actually leave a little bit of a residue. If it's 100 low lead, it just evaporates right away and it's dry. And if it's diesel, it's just like oily and just like stays there a while. It's very oily feeling.
Has a pungent smell.
Yeah. It does. You know what gasoline smells like?
Yes.
It won't smell like that.
Okay, I will notice it.
It won't smell. You will notice it. Yeah. Yeah. So any 100 low lead, any of these smell very similar to the gas you put in your car. This is completely different. Yeah. Okay. All right, let's talk about the heating system real quick. The heating system here, now we're not talking about carburetor, we're going to talk about cabin heat. Okay. The heater in your car, they get that heat off of your radiator, so you've got that coolant running through your engine and getting very, very hot, and they use that to heat your cabin. Most airplanes don't have a coolant system. Now we do in ours, but we don't use it for heat. But most airplanes don't have a coolant system. So what they do, I erase it from here, but you remember that picture of the shroud around the muffler that we pull, or that we don't, but other planes pull. Oh, here. Yeah. Other planes pull the carburetor heat off of this hot air around this muffler. Most GA airplanes, including ours, pull cabin heat. So we have that, and then here's the firewall. We have another little duct that we duct right into the cabin. So we pull warm air off of that muffler and we duct it right into the cabin. That's very dangerous. Anybody understand why that's very dangerous? Carbon monoxide. If there's any cracks in that muffler, we're sending, during the winter time, we've got the heat on, we're bringing that carbon monoxide right into the cabin of the airplane. So you want to be very aware of that. So if you're flying in a GA airplane, so you need to know if you're flying a GA airplane where, and it has a heater, and it's winter, and you've got the heater on, you better know where the heat's coming from. That's why systems is so important in airplanes. Where's that heat coming from? Is it coming off of the muffler shroud? If it's coming off this muffler shroud, be aware that if there's a crack or something compromised on that muffler, you could be getting carbon monoxide in the cabin. Okay? So if you start getting a headache or you start feeling nauseous, I would shut the heater off, open the vents, and get on the ground. Right? So just be aware. You need to be aware of that. Okay?
Do they come out, or are they coming out with any, like electrical systems?
The problem is with airplanes, everything is about weight. Weight is the enemy of an airplane. So you don't have coolant systems on it because it weighs more. You don't have electric heaters because they weigh more, they take a lot of energy. So this is a very efficient way of getting heat. You gotta be aware, you gotta be aware, right? Now, one of the things that you have to do, that we have to do as a flight school, is every 100 hours, well, in summertime, we just take the shroud off. Because we have to inspect the muffler. We're not using heat. And we don't get our carburetor heat from there, so we just take the shrouds off. We put them back on in the wintertime. All right, but when they're on, when we do our 100-hour inspections, we have to take the muffler off, take the shroud off, inspect it, make sure there's no cracks. We have to do all that. Okay. All right, electrical system. So we have in our planes and most GA airplanes, same thing. We have a 12-volt system in our airplane. Could be a 28-volt system or whatever, but ours is 12-volt. And all your electrical system is going to be some type of a DC system. It's either going to have an alternator or a generator. The only difference is that an alternator is AC current. A generator is DC current. So from a practical standpoint, you want to know what it is, because if it's an alternator, then the power output, the voltage output, is going to be more consistent regardless of your throttle setting. If it's a generator, if it's strictly DC, okay, it's a generator, then the higher the throttle setting, the higher the voltage output. The lower the throttle setting, the lower the voltage output. So what do we have in the Rotax engines? We have a generator. It's right here. I'm not going to spin this around again. Remember I was turning the propeller, you saw that flywheel turning back here? That's the generator. That is the generator. So you will oftentimes notice if you land out here and they have you hold up on echo and tell you to contact ground or something, and you're sitting there at idle with all the lights on and everything on, and you try and get on the radio, you're click, 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 you can't get out, you can't communicate. Because there's just not enough voltage in the system. Because you're low RPM and you got all the electric stuff turned on. That can happen sometimes. So if that happens, set the brake, bring the power up, watch your voltmeter come up, and then you get out of the radio. It doesn't happen often, but it might happen to you, so just be aware of it. All right, so we'll have a battery somewhere in the system. We don't need the battery for the electric. Remember, we need the battery only to start it, but it becomes part of the electric system because once we do start, the alternator or generator is going to recharge the battery as we're running. We'll have a master switch somewhere to get the power through everything. Perhaps an alternator or generator switch, bus bar, voltage regulator, blah, 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 stuff like that. You don't need to know a whole bunch about this. What I want you to know from a practical standpoint is how much load are we pulling? All right. And if your generator or alternator dies, what are you going to do? How are you going to deal with that, right? So if you understand a little bit about the electrical system, it helps you understand what to do. Okay, so here's the kind of a schematic. You can have a primary bus, an avionics bus. We have this in our place. We have a master switch, right? We turn on the master switch, and it powers up some things. Once we're running, we turn on the avionics switch, it powers up some other stuff, so we have the same kind of system going here. Think about electric systems like this. I have to use a water analogy. We have voltage, we have amperage. Amperage and current mean the same thing. So think about voltage. Voltage equals pressure or potential. And amperage equals flow, or how fast we're losing what we have stored. So if you look at a water tower, okay? Why do we have water towers all over the place? To create water. So when you turn the hose, when you turn the spigot on, water comes out, right? All right, so you got water up here, okay? And let's say you attach you have a little hose coming out the side that you can turn on and off, okay? All right, this is the voltage or the potential. How much of this do I have, all right? And then I could have a pipe that big or a pipe that big. If I open this pipe and I got this much flow coming out, that's the amperage. So the more amperage I use, the faster I drain the voltage. If I close that one off and I just have a little trickle coming out, that's amperage, but it's going to take a lot longer to deplete the battery, if you will, right? Okay, so think about the voltage as the potential or the amount of pressure that I can develop, and the amperage as, okay, how big of a hose am I draining this out with? Okay? All right, so in the airplane, we have a 12-volt system, right? We have a 12-volt system, and we have a 14-volt generator, and the reason the generator develops 14 volts is because we need it to be able to recharge the battery all the way back up to 12. Okay, so once it depletes, we want to have a little higher voltage recharging so I can get a little higher. All right, so you're going to have somewhere you'll have an ammeter, or we have a voltmeter and ammeters in our airplane, but you'll have an ammeter that tells you whether you're, whether you're discharging or charging, or how many amps you're using. Okay, so as long as the system is working well, you don't have to worry about too much. When you start the engine, assuming you have a full battery, when you start, you crank the engine up and you're going to deplete. By cranking the engine, you open up this big giant guy here to get enough power to get that engine started, and maybe you lose it, and boom, you just put a hit on your battery. Okay. All right, once the engine is started, you stop that voltage output. Okay. And now you're running the rest of the stuff in the airplane, whatever's taken in the airplane. But the generator, in this case, is recharging and bringing that back up to full. Okay? So you're depleting here, but the generator is putting more power back in and keeping your battery topped off, so to speak. But what happens if something happens in our generator or our alternator quits working?
Still have batteries.
But now we start draining. All right, now we start draining. And we're still going to, our lights and our radios and everything are still going to work for some period of time until we drain all that potential out and our battery dies, and now we lose everything.
The engine will still keep running.
The engine keeps, everything electrical, the engine will still keep running. Right. All right.
So like fuel pump,
Electric fuel pump won't run anymore once it's set. Yeah, anything electric is going to stop working. You won't have flaps, you won't have trim.
So you're saying it's wise to get on the ground?
Well,
I mean,
I wouldn't spend a whole lot of time in the year, but there's kind of a way to understand, well, how much time do I have? That's kind of what I want to talk about. First of all, you need to understand, how do I know the generator or alternator went offline? How do I know the ammeter or charging? Well, actually, what's going to happen if you move? Can you move this out of the way? There's a little idiot light on the panel. There's a little idiot light right here, right there. See that little light right there? That guy's going to turn on. If that light is lit, that means that you're operating, everything that's electrical is operating off of the battery. So you should be checking that. It's not on the checklist, but when you go to do your pre-flight inspection, when you go in the cabin, what's the first thing you do? You turn the master switch on so you can check the times and everything. When you turn on that master switch, that means you're drawing electricity. That little light should come on. And that's telling you two things. First of all, the light works. And secondly, that you're drawing power from the battery, okay? And then once you start the engine, that light should go off. And if it goes off...
That light operates on the charge from the generator.
That's right. When that light goes off, that means that you're getting your power, everything electrical is coming from the generator or alternator, if you have an alternator, the power source, okay? All right. So we have a 12-volt system. So we have a 12-volt battery. And so what you want to understand, you need to understand two things. You want to understand the amp hour rating for the battery. So you want the battery's amp hour rating. Okay? And you need to know the amperage. If you know these two things, you know when you're going to run out of juice. Okay?
Considering it's fully charged.
Assuming it's fully charged. You got to take that into account. All right? So let's assume we have a fully charged battery and it has a 12 amp hour rating, or let's call it a 10 amp hour rating, make it easier. Let's say it has a 10 amp hour rating. 10. Okay? And we're drawing 10 amps. Battery's going to die in 1 hour. If we have a 10 amp hour battery, fully charged, and we're drawing 1 amp, it's going to die in 10 hours. If we're drawing 5 amps, it's going to die in 2 hours. Does that make sense?
What do we have on the road tax? The
18.
Yeah, it's an 18 amp hour battery, but think 10.
Safety.
Think 10. Okay?
It's only, but it says only like 50% or 60% of that rating anyway, right?
Well, the amp hour rating, no, what do you mean?
Like those like a typical battery in that, they can only drain down to like 40% or 30%.
No, you'll get the full, if it's a fully charged battery, it'll die at that point. Yeah, right. But the reason I say cut it down to 10 is because it's not a brand new battery probably. Maybe the generator charging system didn't have enough time to bring it all the way back up fully to charge. Maybe you didn't see when the light came on, right? Okay. So just think about load shedding. So if you've got, let's assume you have 10 amps, you have a 10 amp hour battery and your charging system dies and you're pulling 10 amps. We'll start turning things off that you don't need on and watch your amperage flow. Get your amps down as low as you can so that you extend the battery life to get where you got to go. Something along those lines. Okay? All right, we are out of time. Any questions on systems, on what we talked about with systems? We didn't get to, I didn't get to hydraulic systems, but the only thing hydraulic is what? Brakes. That's the only thing hydraulic. The book 808325 goes into other systems that I didn't talk about, pressurization systems, de-icing systems, and stuff like that. Read up on that stuff. We don't have any on our airplanes, and it's not typical to have pressurization systems on smaller GA airplanes, or de-ice or anti-ice systems on smaller GA airplanes. Oxygen systems, we didn't talk about. So there's a number of things we didn't talk about. So make sure you read the rest of the chapter that I was unable to get to. All right, next week is flight instruments and manuals and documents. So that is chapter 8. So read chapter 8 and come with questions. Did I answer the question? The only question I have is road tax specific. I think I went into, I don't remember who asked that, but I think I went into differences on the road tax stuff. Yeah.
I didn't realize it had two carburetors.
Yeah, two carburetors, yeah. Okay, very good. I'll see you guys next week. The fair's next week, so come out and see us at the fair.